Hello there. On a quiet night, you look up. The cosmos above feels vast, ancient, and alive with infinite possibility. Sometimes, a celestial phenomenon arrives that challenges our settled perspectives. Tonight, our attention turns to a truly rare visitor. The interstellar object designated 3I, Atlas. It has recently captivated astronomers worldwide. This distant wanderer has exhibited sudden, unexpected changes in its observed behavior. These transformations are unlike anything seen in typical cometary activity. Such anomalies ripple through our understanding of the universe. They compel us to reconsider what we thought we knew about objects from beyond our solar system. What if this enigmatic visitor signals something more profound than just another icy comet passing through? Could its rapid and peculiar alterations suggest an origin far removed from natural astrophysical processes? Perhaps its appearance hints at a deliberate trajectory, a controlled passage. What might the very latest observations reveal about its true journey across the galactic void? What secrets does its unique composition hold? And what could its presence, with its unsettling changes, ultimately imply for our own place within the cosmic tapestry? We are invited to carefully follow the subtle, intriguing trail of this extraordinary object. Let us together uncover what this rare visitor might truly mean. Let's dive in and explore how it all unfolds. From the initial whisper of an unknown cosmic presence, our gaze now sharpens on 3I, Atlas. The universe frequently sends us enigmatic visitors, and this particular object demands our most focused attention. 3I, Atlas, emerges as a celestial body, unlike typical residents of our solar system. It is, by definition, an interstellar interloper, charting a distinct, hyperbolic trajectory through our immediate celestial neighborhood. This unique orbital path confirms its origin beyond the Sun's gravitational dominion, marking it as a transient guest from the vast, star-strewn reaches between stellar systems. Its official designation, 3I, explicitly identifies it as only the third confirmed interstellar object ever detected by human instruments. This classification immediately sets it apart, indicating it formed around another star, traveled untold light years, and now briefly passes through our cosmic home. Its very presence challenges fundamental assumptions about the composition and dynamics of objects within our own solar system. Before the arrival of 3I, Atlas, two other celestial wanderers profoundly challenged our understanding of cosmic visitors. The first, 1I Oumuamua, discovered in 2017, appeared as a peculiar, elongated shape, often described as cigar-like or pancake-shaped, tumbling through space. It baffled scientists with its complete lack of cometary activity, displaying no discernible dust or gas tail. Its unexpected non-gravitational acceleration further fueled intense scientific debate. Then came 2I, Borisov in 2019, which, while also interstellar, presented as a more conventional-looking comet, exhibiting a clear coma and tail. It was composed of common cometary gases, though its pristine nature suggested an origin from a colder, more distant stellar system than our own. Both Oumuamua and Borisov were fleeting, enigmatic visitors, yet they fundamentally redefined the boundaries of what we might expect from objects traversing interstellar space. 3I, Atlas now extends this nascent lineage, yet it presents an entirely new set of puzzles, pushing the limits of astronomical classification even further. It forces a re-evaluation of established models for cometry and asteroidal behavior, as if a silent messenger from an alien world, carrying secrets etched into its very being. 3I, Atlas compels astronomers to redraft their existing models of small body formation and evolution. Its existence questions our neat, often anthropocentric, categories of cosmic phenomena. academic tension builds within the scientific community. When its observed size, peculiar trajectory, and complex, often contradictory, chemical signatures do not neatly fit established cometry or asteroidal archetypes. The accumulating data consistently defies simple, conventional explanations. One particularly revealing recent dataset confirms its closest solar passage occurred at approximately 2 astronomical units from the Sunday. This distance is roughly equivalent to the average orbital radius of Mars, placing it well within the inner solar system. At its closest approach, 3I, Atlas, passed within 300 million kilometers of our star. To put this into perspective, this distance is more than 7,500 times the circumference of Earth, a vast cosmic gap that still allowed for detailed observation. Such a journey would take a modern jetliner over 3 decades to traverse. The intricate story of 3I Atlas began with its initial faint detection by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a sophisticated network of robotic astronomical survey telescopes. These instruments are designed to continuously scan the night sky, identifying any moving objects that might pose a threat to Earth. The first subtle signal appeared in deep sky images, captured on a specific date in late 2023, initially catalogued as a routine near-Earth object with a provisional designation. However, subsequent rapid-fire observations from other major survey projects, including Pan-STARRS and the Zwicky Transient Facility, quickly revealed its highly unusual orbital parameters. Astronomers at various international institutions then collaboratively cross-referenced these preliminary findings. They meticulously tracked its precise motion against the fixed backdrop of distant stars over several nights. This rigorous astrometric analysis definitively confirmed its hyperbolic trajectory, a telltale signature of objects not gravitationally bound to our Sunday. This rapid progression from initial detection to definitive classification as an interstellar object highlights the advanced state of modern astronomical surveys and the efficiency of global observatory networks. The speed of confirmation was unprecedented, allowing for early, intensive follow-up campaigns, unraveling the profound secrets held within 3I. Atlas demands a comprehensive suite of sophisticated observational methods and cutting-edge instrumentation. Ground-based telescopes, often equipped with powerful adaptive optics systems, provide exceptionally high-resolution imaging, allowing astronomers to resolve fine details of its evolving coma and, potentially, its central nucleus. Spectrographs are crucial tools. They analyze the light reflected or emitted by the object, breaking it down into its constituent wavelengths, much like a prism separates white light into a rainbow. This process reveals the object's precise chemical composition, identifying specific spectral lines that correspond to various molecules, such as water ice, carbon dioxide, carbon monoxide, or complex organic compounds. Infrared spectroscopy, in particular, probes the thermal emissions and vibrational modes of molecules, offering insights into volatile content, while radio telescopes continuously search for any faint, anomalous radio emissions. None have been definitively linked to 3I Atlas, maintaining its natural celestial identity. Space-based observatories, such as the venerable Hubble Space Telescope and the James Webb Space Telescope, offer unparalleled clarity, operating above the distorting effects of Earth's atmosphere. They track subtle long-term changes in its brightness, morphology, and the expansion rate of its dust and gas tails. Astrometry, the precise measurement of star and object positions over time, is fundamental for refining its orbital path with extreme accuracy, allowing for robust predictions of its future movements and detailed reconstructions of its past trajectory. through interstellar space. Each distinct method contributes a unique, indispensable piece to the complex, evolving puzzle of 3I Atlas. The arrival of 3I Atlas gains profound scientific and philosophical context when viewed through the lens of its interstellar predecessors. 1I Oumuamua, the very first confirmed interstellar visitor, discovered in 2017, presented as a truly enigmatic object. A tumbling, elongated body, perhaps 400 meters in length, devoid of any visible coma or cometary activity. Its most perplexing feature was a persistent, unexplained, non-gravitational acceleration, which could not be accounted for by simple outgassing. This anomaly sparked intense debate, with theories ranging from the outgassing of unseen volatiles like molecular hydrogen to more speculative, though eventually discounted, artificial origins. 2I Borisov, in stark contrast, discovered in 2019, behaved much more like a typical comet, displaying a distinct coma and tail composed of common cometary gases such as cyanogen and carbon monoxide. Its composition hinted at a remarkably pristine nature, suggesting it originated from a colder, more distant stellar system than our own, having avoided significant processing. These two objects established a crucial, albeit limited, baseline for interstellar object characteristics. Oumuamua challenged our understanding of form and dynamics. Borisov affirmed cometary norms from afar. 3I Atlas now occupies a fascinating middle ground, exhibiting clear cometary activity, but with unexpected patterns and chemical ratios. Its observed dust trails, for instance, do not conform to standard cometary models, suggesting either an unusual, perhaps exotic composition, or a complex, poorly understood interaction with solar radiation and the solar wind. Studying these diverse analogues provides astronomers with a vital comparative framework, allowing them to refine their search for commonalities, divergences, and the truly unique attributes among interstellar travelers. The persistent presence of interstellar objects like 3I Atlas ignites profound philosophical reflections across both scientific and public spheres. These objects are not merely celestial debris. They are tangible fragments from other star systems, offering a direct, if silent, connection to the wider galactic tapestry. Their existence compels us to confront our cosmic isolation and consider the sheer abundance of planetary and protoplanetary material distributed throughout the Milky Way. What untold stories do these silent wanderers carry from their distant homes? Do they harbor clues about the processes of planet formation around other stars? Could they even hint at other biospheres, other forms of evolution, or even the potential for complex life beyond Earth? The rigorous study of these objects transcends mere astrophysics. It delves into fundamental questions about the origins of matter, the universality of physical laws across the cosmos, and the profound potential for life elsewhere in the universe. They serve as cosmic ambassadors, prompting humanity to expand its perspective on its own place within the vast, often indifferent, universe. The very concept of familiar versus unfamiliar is fundamentally challenged by these transient, enigmatic guests from beyond our stellar doorstep. They are reminders of the boundless, unexplored frontier. Intriguingly, early spectral data from 3I Atlas suggested a significantly higher than expected ratio of diatomic carbon, C2, compared to water, H2O, a chemical signature more commonly associated with older, dynamically evolved comets found within our own solar system, rather than a pristine, freshly arrived interstellar object. This unexpected blend of elements adds another perplexing layer to its already mysterious profile. As the data continues to accumulate and new observations refine our understanding, you watch astronomers piece together this intricate cosmic narrative. We will next delve deeper into the precise moments of its initial discovery, the advanced techniques continuously employed to observe it, and how its unique, often contradictory, characteristics challenge every model and classification scheme we currently hold. Having peered into the enigmatic nature of 3I, Atlas, and the unsettling implications of its observed transformations, our understanding now demands a return to its genesis. We must trace the path of this extraordinary celestial wanderer back to the very first flicker of its detection, understanding how it materialized from the cosmic background into our scientific consciousness. This journey begins not with a grand announcement, but with the diligent, tireless work of automated sentinels scanning the vast, dark expanse above, patiently awaiting the subtle signs of an unexpected visitor. The object known as 3I, Atlas, a designation signifying its status as the third confirmed interstellar visitor to our solar system, first registered its presence on 1 July 2025. The discovery originated from the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This sophisticated robotic survey network, comprising multiple telescopes, strategically located in both the northern and southern hemispheres, specifically in Hawaii and Chile, operates with a singular, vital purpose. It systematically sweeps the entire observable sky several times each night, meticulously searching for moving objects that might pose a collision threat to Earth. Its wide-field cameras, equipped with advanced CCD detectors, capture vast swathes of the cosmos, processing terabytes of raw image data, with sophisticated algorithms designed to identify subtle shifts against the immutable backdrop of distant stars. The system is a frontline defense, its vigilance a testament to humanity's growing awareness of its cosmic neighborhood. On that particular July morning, the Chilean Atlas unit, situated high in the arid Atacama Desert, captured a series of images containing an anomalous point of light. The automated detection software, programmed to flag any deviation from known celestial mechanics, registered an object exhibiting an unusual, highly accelerated trajectory. This was no ordinary, gravitationally bound asteroid or comet, following a predictable elliptical path around our Sun, nor was it a known artificial satellite. Subsequent, rapid analysis of its precise astrometric measurements confirmed a definitive hyperbolic trajectory. This specific mathematical curve, characterized by an orbital eccentricity greater than 1, is the unmistakable signature of an object possessing too much kinetic energy to be captured by the Sun's gravity. It means 3I, Atlas, unequivocally arrived from interstellar space, merely passing through our solar system, destined to continue its solitary voyage into the immense galactic void, never to return. The implication of this discovery was profound. A truly alien object, born in the crucible of another star system, had entered our local cosmic neighborhood. Its arrival was swift, a high-speed transit, offering minimal warning to Earth-based observers. Unlike long-period comets that might be spotted years, even decades, in advance as they approach from the Oort cloud, or asteroids with well-charted, repetitive orbits, interstellar objects like 3I, Atlas appear suddenly. They move at velocities that make early detection incredibly challenging, often becoming visible only when relatively close to the Sun, or, in this case, when already well within the inner solar system. They are, in essence, cosmic bullets, traversing incomprehensible distances with little to announce their approach until they are upon us. This inherent stealth makes them both scientifically thrilling and a potential, if rare, planetary defense concern. The scientific community, accustomed to the predictable, clockwork dance of our solar system's inhabitants, experienced a familiar jolt of excitement Mixed with intense academic tension, interstellar visitors are theoretically predicted by sophisticated models of planetary formation and stellar dynamics. Countless small bodies are ejected from young star systems during their chaotic, violent formation phases. These ejected fragments then drift for eons through the galactic medium. Yet, despite these strong theoretical predictions, their actual observation remains an exceedingly rare event, a testament to the sheer emptiness of space and the difficulty of spotting such small, fast-moving objects. Before 3I, Atlas, only 2 such objects had been unequivocally confirmed: Oumuamua in 2017 and Comet Borisov in 2019. Oumuamua, famously cigar-shaped and exhibiting puzzling non-gravitational acceleration without visible outgassing, sparked intense debate about its possible artificial origin, challenging astronomers to consider truly exotic explanations. Borisov, a more conventional comet, still provided invaluable insights into the composition of another star's protoplanetary disk, offering a direct sample of extrasolar material. Each new detection serves as a unique, fleeting opportunity, a spotlight moment that fundamentally reshapes our understanding of the universe beyond our immediate stellar sphere, pushing the boundaries of what we thought possible. Imagine the vast, silent expanse of interstellar space, punctuated by the occasional flare of a distant star, a timeless void where countless untold stories unfold, as though a silent, cosmic voyager had suddenly appeared on the edge of our celestial map. 3I, Atlas, emerged from this profound darkness. Its initial detection was almost an act of serendipity, a faint signature in a deluge of data, easily lost among the millions of other celestial objects. The Atlas system, designed for high-cadence, wide-area scans, processes images so rapidly that a human observer could easily overlook such a subtle anomaly amidst the countless stellar points. The object's true, extraordinary nature only became apparent after the algorithms flagged its unusual motion, prompting human astronomers to dive into the raw data for meticulous verification. This quirky detail, that such a significant discovery began as a mere computational flag, a statistical outlier in a robotic survey, highlights the fascinating blend of advanced automation and critical human ingenuity that defines modern astronomical discovery. It underscores how our instruments extend our senses far beyond what was once conceivable. At the moment of its initial detection, 3I, Atlas was already more than 1.5 astronomical units from Earth. To contextualize this immense distance, 1.5 AU translates to approximately 225 million kilometers, a span significantly greater than the average distance between Earth and Mars at their closest approach. Moreover, it was hurtling through space at an astonishing velocity, estimated to be in the range of tens of kilometers per second. To put this speed into a tangible perspective, at 20 kilometers per second, 3I, Atlas, could traverse the entire width of the continental United States, from the Atlantic coast to the Pacific, in under 4 minutes. This immense speed, coupled with its hyperbolic trajectory, meant that the window for detailed observation would be relatively brief, necessitating an immediate and highly coordinated global response from the world's leading astronomical facilities. Every hour counted as it moved swiftly towards its perihelion, its closest approach to the Sun, before receding into the depths. The initial Atlas flagging triggered a rapid, worldwide mobilization of astronomical resources, a testament to the agile, interconnected nature of contemporary science. The venerable Hubble Space Telescope, orbiting high above Earth's distorting atmosphere, was among the first space-based assets to be directed towards 3I Atlas. Its wide-field camera, 3WFC, 3. Provided exquisitely sharp, visible light images, crucial for determining the object's apparent size, its precise rotation period, and any early signs of cometary activity, such as a faint coma or developing tail. These early, high-resolution observations were vital for understanding its initial physical characteristics and morphology, before it receded further and its appearance potentially changed. Almost concurrently, the revolutionary James Webb Space Telescope, strategically positioned at the Earth-Sun L2 Lagrange point, began its infrared observations. Webb's suite of instruments, including the near-infrared spectrograph and the mid-infrared instrument, MIRI, were deployed to probe 3I, Atlas's thermal signature and detailed chemical composition. By analyzing the infrared light emitted and reflected by the object, scientists could deduce its surface temperature, the precise presence and abundance of volatile compounds, like water, ice, carbon dioxide, or methane, and the composition of any dust or gas emanating from its surface. These infrared insights are absolutely crucial for understanding the conditions in its home star system and the processes it might have undergone during its long interstellar journey. Complementing these powerful space-based assets, a vast network of ground-based observatories across the globe joined the concerted effort. Telescopes equipped with cutting-edge adaptive optics in Hawaii, such as the twin Keck Observatory telescopes and the Very Large Telescope in Chile, provided unparalleled high-resolution imaging and continuous astrometric measurements. These measurements refined the object's precise trajectory with unprecedented accuracy, allowing for more precise predictions of its future path. Spectrographs attached to these powerful instruments began to dissect the light reflected from 3I, Atlas, across various wavelengths, from ultraviolet to radio. These intricate spectral fingerprints offered invaluable clues about the surface materials, revealing the elemental and molecular composition of its enigmatic exterior, searching for unusual compounds or unexpected signatures. The global astronomical community, from professional observatories to dedicated amateur enthusiasts, collaborated tirelessly, sharing data and insights in a frantic race against time, knowing that this was a once-in-a-lifetime opportunity. The academic tensions surrounding 3I, Atlas, only intensified with each new data point, particularly as the rapid changes detected began to manifest. Were these changes natural cometary activity, perhaps stemming from previously unknown, deeply buried volatiles reacting to solar heating? Or did they suggest something far more unusual, something defying conventional astrophysical models? The possibility of a controlled object, a hypothesis whispered cautiously but persistently in scientific circles, pushed the boundaries of conventional astrophysical interpretation to their absolute limits. This radical idea, though highly speculative and requiring extraordinary evidence, forced astronomers to confront the full spectrum of possibilities, challenging them to consider whether the universe held secrets far stranger than currently imagined. The detection of 3I, Atlas, became not just a scientific observation, but a profound philosophical reflection on our place in a potentially teeming galaxy and the implications of encountering technology from beyond our star. The debate raged, fueling both skepticism and intense curiosity. The collective efforts of these diverse instruments, from the initial automated flag to the sophisticated spectral analysis, began to paint an increasingly detailed, yet still profoundly perplexing, portrait of 3I, Atlas. Its journey through our solar system, brief and enigmatic, provided a unique, albeit challenging, opportunity to study an object born in another star system. This initial glimpse, however, was merely the overture to a much larger, more complex symphony of observation and discovery. Now, we turn our attention to how these varied and powerful observation methods themselves began to reveal the hidden, often contradictory details of this extraordinary cosmic traveler, peeling back layers of mystery, one spectral line at a time. The enigma of 3I. Atlas deepens with each passing day, its rapid transformations challenging our very understanding of interstellar objects. To truly grasp its elusive nature, you must first comprehend the vast, interconnected network of instruments astronomers now wield, extending humanity's reach across the cosmic ocean. This meticulous observational effort forms the bedrock of our knowledge. 3I. Atlas, the interstellar object, currently under intense scrutiny, presents a dynamic and perplexing cosmic puzzle. Its swift and unpredictable changes demand constant vigilance, pushing the limits of current observational science and the ingenuity of its practitioners. This transient visitor offers a unique, fleeting opportunity for discovery, prompting a global scientific response. Its classification remains uncertain, fueling intense research efforts worldwide. Astronomers deploy an intricate array of sophisticated instrumentation, each meticulously designed to capture different facets of this distant wanderer. The initial detection of such objects often falls to wide-field survey telescopes. These ground-based automated systems scan vast swathes of the night sky. They look for moving points of light against static star fields. Once identified, the follow-up observations begin in earnest. Spaceborne assets like the revolutionary James Webb Space Telescope, or JWST, peer into its infrared signature. JWST's near-infrared camera, NIRC, and mid-infrared instrument, MIRI, offer unparalleled sensitivity. They allow scientists to detect faint heat emissions. They also identify specific molecular compounds, such as water, ice, carbon dioxide, or even complex organic molecules. These detections are possible even from extreme distances, reaching into the outer solar system. By analyzing absorption and emission lines in the infrared spectrum, researchers can map the volatile composition of 3I, Atlas's coma. This provides crucial clues about its internal structure and activity. The presence and ratios of these volatiles, like the carbon monoxide to water ratio, are key indicators. They help differentiate between cometary types and their origins. The venerable Hubble Space Telescope, with its keen vision, invisible and ultraviolet light, captures 3I, Atlas's intricate morphology. Its wide-field camera, 3WFC3, and Advanced Camera for Surveys, ACS, reveal any developing comets or nascent tail structures with exquisite detail. Hubble's observations are vital for tracking the object's brightness variations, or light curve. These curves can indicate rotation, tumbling, or the episodic expulsion of material. Precise astrometry, the measurement of its exact position over time, is also performed with Hubble. This data allows for the continuous refinement of its orbital parameters. It helps predict its future path through our solar system. From Earth, giant observatories such as the Gemini South Telescope in Chile, equipped with advanced adaptive optics, track its precise motion through the night sky. Adaptive optic systems compensate for atmospheric distortion. They use deformable mirrors and laser-guide stars. This allows ground-based telescopes to achieve near space-based resolution, overcoming terrestrial blurring. Gemini's spectroscopic capabilities provide high-resolution data on gas emissions and dust composition. These ground-based telescopes offer continuous monitoring, crucial for refining orbital parameters and detecting subtle shifts in trajectory. They also provide a higher cadence of observations than space telescopes. Together, these diverse instruments function as a global surveillance system, They meticulously record its every subtle alteration, from minute brightness fluctuations to changes in its spectral composition and kinematic behavior. The sheer volume of data collected is immense. It is as if humanity has woven a delicate, invisible web across the solar system. Each strand, a beam of light. Each knot a powerful lens collecting ancient photons. This intricate network of cosmic sensors records 3I, Atlas's precise light curve, mapping its brightness variations over time, sometimes revealing periodic changes. They analyze its spectrum, which acts as a unique chemical fingerprint, revealing the specific elements and molecules vaporizing from its surface. They also track its motion with astonishing precision, charting its path against the backdrop of distant stars. These collective, multi-wavelength observations build a comprehensive, multi-dimensional portrait of this enigmatic visitor. Piece by painstaking piece, this mosaic of data paints a picture no single instrument could achieve alone. One concrete data point, emblematic of this relentless observational effort, emerged from this vigilant watch. Hubble's keen eye captured a crucial image of 3I Atlas on 21 July 2025. At that precise moment, the object resided at a staggering distance of 277 million miles from Earth. This vast separation, approximately 1.85 astronomical units, is an immense expanse of space. To put that into perspective, imagine a journey equivalent to circling Earth's equator 11,000 times. That immense distance, a voyage lasting over a century for a modern jetliner, separates us from this enigmatic wanderer. The faint light from 3I Atlas, traveling at 299,792,458 meters per second, takes nearly 25 minutes to reach our detectors. This delay highlights the challenge of real-time observation and rapid decision-making in astronomical emergencies. This unprecedented level of coordinated observation echoes the intense study of Oumuamua, the first confirmed interstellar visitor detected in 2017. That object displayed peculiar non-gravitational acceleration, baffling scientists who could not attribute it to typical cometary outgassing. Its highly elongated shape and apparent lack of a cometary tail defied easy categorization. This sparked fervent debates about its true nature. Some theories even posited exotic explanations, including the possibility of artificial origin, though mainstream science largely dismissed these as speculative. The scientific community grappled with a truly alien object. Then came 2I Borisov in 2019, the second confirmed interstellar object. Borisov behaved more like a conventional comet. It exhibited a dusty coma and a clear tail of gas. Its spectrum revealed common cometary volatiles, such as cyanogen and diatomic carbon. This provided a stark contrast to Oumuamua's inert appearance. Borisov offered a reassuring, albeit still extraordinary, glimpse of a normal interstellar comet. Now, 3I Atlas presents a new puzzle. It shows rapid changes reminiscent of cometary activity, yet exhibits trajectory deviations that complicate a simple cometary classification. Its behavior seems to occupy a middle ground, or perhaps an entirely new category, between the two previous interstellar visitors. This comparative analysis is crucial for understanding its unique characteristics and its place in the interstellar object population. Each new visitor refines our understanding of galactic wanderers. Observing objects like 3I Atlas requires more than just powerful telescopes. It demands a global ballet of scheduling and scientific diplomacy, often under immense pressure. Precious observation time on these multi-billion-dollar instruments is fiercely negotiated among competing research teams. sometimes years in advance. Yet, for rapidly evolving phenomena like 3I, Atlas, astronomers often employ a technique called target of opportunity, or 2O observations. This allows them to interrupt meticulously planned, long-term research programs to capture fleeting, urgent events. This constant reprioritization, often involving sleepless nights for telescope operators and scientists across different continents, highlights the profound scientific interest and the unpredictable nature of interstellar phenomena. The competition for these brief windows of observation creates a unique, high-stakes scientific environment. It underscores the global, collaborative nature of modern astronomy. The academic tension surrounding 3I, Atlas, intensifies with each new dataset. Astronomers meticulously gather and share. Its recorded brightness variations, spectral characteristics, and evolving tail formation do not comfortably match the established models for known comets or asteroids from our own solar system. While some aspects suggest cometary activity, the scale, rapidity, and asymmetry of these changes are unusual. This challenges our existing paradigms for cometary evolution. Furthermore, subtle, persistent deviations in its trajectory raise profound questions about the presence of non-gravitational forces. For a typical comet, these forces are attributed to the rocket-like thrust from outgassing volatiles as the Sun warms its surface. However, the magnitude or direction of these forces for 3I Atlas appears inconsistent with standard cometary sublimation models. Researchers are openly debating whether these deviations indicate an unusual composition, an asymmetric outgassing pattern, a highly porous structure, or perhaps something entirely different. This something different could involve exotic physics or an unknown internal mechanism, pushing the boundaries of our current understanding. The discomfort among researchers is palpable as they grapple with data that resists conventional explanation, prompting a re-evaluation of fundamental assumptions about cosmic wanderers. These detailed observations, meticulously collected and painstakingly analyzed, compel us to widen our view beyond mere classification. We must compare 3I Atlas not only to prior celestial analogues but also anchor its place within the grand, evolving cosmic narrative. Interstellar objects serve as messengers from other star systems, carrying invaluable clues about their formation and evolution. They provide tangible samples of matter from beyond our Sun's influence, offering a direct window into the chemistry of other stellar nurseries. The universe continually presents phenomena that stretch our understanding, inviting deeper inquiry into the formation of planetary systems, the dynamics of galactic travel, and the very composition of matter beyond our stellar neighborhood. This object forces us to confront the unknown, expanding our cosmic perspective and reminding us of the vastness of what remains to be discovered. It challenges us to refine our models of cosmic wanderers and the processes that shape them across the galaxy. This is a story of cosmic discovery unfolding in real time. As we continue to gather these precious data points, the true nature of 3I Atlas slowly begins to coalesce, guiding us toward its ultimate classification and perhaps revealing a deeper secret about the interstellar medium itself, awaiting its turn in the cosmic spotlight. The next step is to examine its place among other cosmic wanderers. The initial fleeting glimpses of 3I Atlas, much like its predecessors, offered only fragments of a larger cosmic narrative. These early observations, meticulously gathered through tireless sky surveys and dedicated telescopic campaigns across continents, began to hint at an object unlike any previously encountered. They set the stage for a deeper, more rigorous examination of its truly unique characteristics, compelling astronomers to look beyond familiar frameworks and embrace novel interpretations. The very act of detection initiated a profound shift in our understanding of interstellar wanderers and the dynamic nature of galactic exchange, pushing the boundaries of known celestial mechanics. This particular celestial body, formerly designated 3I, Atlas, now stands as the third confirmed interstellar visitor to chart a temporary yet significant course through our inner solar system. Its extraordinary journey from beyond our sun's gravitational embrace makes it an exceptionally rare and invaluable specimen for scientific study, a pristine relic from another star. Its fleeting presence here offers an unparalleled opportunity to directly probe the composition, dynamics, and evolutionary history of distant star systems, providing tangible, measurable evidence of ongoing galactic material exchange across vast cosmic distances. Before 3I, Atlas truly captured our collective scientific attention, two other interstellar guests had already made their indelible marks upon astronomical understanding, reshaping our cosmic perspective. The first, 1I Oumuamua, discovered in 2017 by the Pan-STARRS telescope in Hawaii, presented itself as an elongated, cigar-shaped enigma. A truly alien form, its profound lack of a discernible cometary tail, even as it swung close to the sun and experienced significant solar heating, deeply puzzled astronomers worldwide. Initial observations, painstakingly analyzed, revealed an object with an extreme aspect ratio, estimated to be up to 10:1, making it unlike any known solar system asteroid or comet. Scientists scrambled to explain its peculiar non-gravitational acceleration, which suggested outgassing but without any visible coma, a paradox that fueled intense speculation. Hypotheses ranged from the sublimation of exotic, unseen hydrogen ice to truly exotic, non-natural origins, sparking intense public and academic discourse. Oumuamua defied easy classification, challenging every preconceived notion of what an interstellar object should be, forcing a complete re-evaluation of our observational biases and expected characteristics for these galactic travelers. Then came 2I Borisov in 2019, discovered by amateur astronomer Gennady Borisov, a testament to citizen science. This object offered a contrasting, yet equally significant perspective on interstellar visitors. Borisov behaved much like a typical solar system comet, actively outgassing and displaying a clear, luminous coma and tail as it approached perihelion. Its familiar cometary activity, including strong emission lines from cyanogen and diatomic carbon, provided a reassuring parallel to objects formed within our own solar system's Oort cloud. The spectral analysis of Borisov indicated a composition largely similar to comets from the outer reaches of our own system, albeit with some minor differences in volatile ratios, suggesting slight variations in its birthplace. These two objects, Oumuamua and Borisov, collectively established an initial, albeit broad and somewhat contradictory, baseline. They defined the early, perceived boundaries of what an interstellar visitor might look like and how it might behave, from inert rock to active comet, from a mysterious cigar to a familiar fuzzy ball. Yet, 3I Atlas immediately began to challenge these established frameworks with its own distinct set of behaviors and observed properties. Its characteristics suggest an object fundamentally different from both its predecessors, occupying a new niche. Early estimates, derived from its exceptional brightness and persistent activity, indicate it might be substantially larger than both Oumuamua and Borisov, potentially spanning several kilometers across, perhaps even approaching the size of a small asteroid from our own system, a true behemoth among interstellar guests. Its activity levels are notably higher, exhibiting a persistent, vigorous outgassing and a pronounced brightness that surprised observers even at significant distances from the Sun, where most comets would be dormant. This unexpected dynamism, coupled with its rapid changes in brightness and morphology, forces a profound re-evaluation of our assumptions about interstellar matter. The very existence of 3I, Atlas, broadens the known spectrum of interstellar objects, pushing the boundaries of what we thought possible for these galactic nomads and their diverse origins. It suggests a richer diversity of formation environments and compositional outcomes across the Milky Way than our current models had anticipated, opening new avenues for theoretical exploration. It is as if this object holds a distant, perfectly polished mirror, reflecting the diverse conditions and truly unique formative processes of another star system's birth back upon our own cosmic backyard, a silent testament to galactic variability. Its fleeting presence offers a unique and invaluable chance to glimpse the raw materials, volatile inventories, and dynamic processes that shaped worlds far beyond our immediate stellar neighborhood, providing a tangible, albeit indirect, link to alien nurseries and their distinct chemical signatures. The peculiar combination of 3I, Atlas's hyperbolic trajectory, its estimated substantial size, and its intense, variable activity, has created a significant and palpable academic tension within the astrophysics community. These enigmatic attributes defy simple categorization, sparking vigorous, often contentious, and highly technical debate among planetary scientists, astrodynamicists, and theoretical modelers who grapple with its implications. The central challenge lies in reconciling these unprecedented observations with existing models of cometry and asteroidal evolution, pushing the limits of our current understanding of cosmic chemistry, dynamics, and the very processes of planet formation across the galaxy. One particularly striking and revelatory detail emerged from a recent compositional study, illuminating 3I, Atlas's truly unusual chemical makeup with remarkable clarity. This meticulous research, utilizing advanced spectroscopic techniques from powerful ground-based telescopes, measured the CO₂-to-water ratio within the object at approximately 8:1. This proportion is profoundly and remarkably higher than what is typically observed in comets originating from our own solar system's Oort cloud or Kuiper belt, where water ice usually dominates, often by factors of hundreds. Such a dominant carbon dioxide signature points definitively to formation conditions drastically different from those prevalent in our immediate stellar neighborhood. It strongly suggests a much colder, perhaps more carbon-rich environment in its birth system, fundamentally altering our understanding of extrasolar volatile inventories and the chemistry of other protoplanetary disks, providing a critical, quantifiable clue to its distant origins and its journey through interstellar space. To truly grasp the sheer, mind-boggling scale of the distances involved in these cosmic encounters, consider the following relatable analogy. Even at its closest approach, 3I Atlas remains many millions of kilometers away from Earth, a distance that dwarfs everyday human experience and comprehension. This immense separation is roughly equivalent to navigating the globe more than 100 times, a continuous journey no human has ever completed. Even in the most advanced, long-duration spacecraft, the light from 3I Atlas, traveling at the astonishing speed of 300,000 kilometers per second, still takes several minutes to traverse the vast, empty void and reach our most powerful ground-based and spaceborne telescopes. This inherent, unavoidable delay underscores the immense vastness of space and the profound challenges inherent in remote observation, requiring immense patience, sophisticated data processing, and highly sensitive instrumentation to glean its secrets. Observers also noted an unusual, rapid, and seemingly unpredictable brightening cycle in 3I Atlas, a photometric behavior not easily explained by simple rotational dynamics alone. This erratic variability, sometimes occurring over mere hours or even shorter timescales, hints at complex and perhaps violent surface processes. It could indicate sudden, explosive, volatile outbursts from pockets of highly pressurized gas beneath its crust, or even suggest a highly irregular, tumbling shape that presents rapidly varying cross-sections to our view. The light curve variations consistently suggest a dynamic, ever-changing surface, adding yet another layer of profound mystery to its already enigmatic character and its interstellar origin story, challenging our standard models of cometary activity. You watch as these celestial wanderers, particularly the enigmatic 3I Atlas, profoundly challenge our fundamental understanding of planetary system evolution and galactic chemistry, forcing a re-evaluation of established scientific dogma. Each new object arriving from beyond our sun's gravitational well offers a unique, invaluable data point, a pristine cosmic sample from an alien environment, untouched by our solar system's influence. They collectively suggest that the building blocks of planets, the icy and rocky debris found in protoplanetary disks, vary far more wildly across the galaxy than previously imagined, shattering our comfortable, Earth-centric assumptions about cosmic uniformity. This profound variation invites deep philosophical questions about cosmic commonality, the prevalence of life, and the sheer uniqueness of individual stellar nurseries throughout the vastness of the cosmos. Are the specific processes that shaped our solar system, leading to its particular arrangement of planets and its specific volatile reservoirs, truly universal throughout the Milky Way? Or do countless, unique pathways exist for the birth of stars and their accompanying worlds, each yielding distinct chemical and physical compositions, dictated by local conditions, stellar metallicity, and even the proximity of supernovae? The very existence of 3I Atlas, with its anomalous CO₂ ratio and surprisingly high activity, broadens our cosmic perspective significantly. It compels us to consider the vast, unexplored diversity of the universe's formative environments, pushing the boundaries of our theoretical models and requiring new computational simulations. It reminds us that our own solar system, with its familiar comets and asteroids, is but one example among billions. A single data point in an ocean of possibilities, perhaps even an outlier in some respects. This object acts as a silent, yet eloquent messenger. It carries chemical secrets and dynamic behaviors from an alien nursery, millions of years in its past, offering a tangible, albeit indirect, connection to another star's distant formation and its unique history. Its presence prompts us to fundamentally reconsider the commonality of certain chemical compositions within planetary systems across the galaxy, especially concerning the ratios of key volatiles. It makes us question the prevalence of specific volatile elements, like the balance between water ice versus carbon dioxide ice, which are crucial for the development of atmospheres, oceans, and potentially the emergence of life. The stark differences observed in 3I Atlas, compared to both Oumuamua's inertness and Borisov's more typical cometary nature, are not merely scientific curiosities to be catalogued in a database. They represent distinct chapters in the grand unfolding story of galactic formation and evolution. They hint at different stellar nurseries, perhaps even different stellar populations or metallicities, and entirely different planetary architectures, challenging our existing paradigms and requiring entirely new theoretical frameworks. You find yourself contemplating the immense variety of cosmic environments that could produce such an object that defies our established categories and pushes the limits of our imagination. The established frameworks we have built for understanding comets and asteroids, based largely on observations within our own solar system, are stretched thin, even broken, by these interstellar interlopers. They force us to adapt, to expand our theoretical models, and to embrace a more flexible, open-minded view of cosmic origins and the potential for unexpected phenomena. This continuous recalibration of scientific understanding, driven by unexpected discoveries like 3I Atlas, is a hallmark of true intellectual progress. It is precisely how knowledge truly advances, pushing beyond the comfortable boundaries of the known and into the realm of the truly novel and astonishing. The journey of 3I Atlas through our system is a profound lesson in cosmic humility, reminding us of our limited perspective and a boundless source of wonder, underscoring the fact that the universe holds endless, breathtaking surprises, waiting patiently to be discovered, meticulously analyzed, and ultimately understood by curious minds across generations. This cosmic dance of discovery never truly ends, inviting us ever deeper into its mysteries. From this expanded context, enriched by comparisons to its interstellar predecessors and deep philosophical reflection on galactic diversity and the uniqueness of cosmic origins, we now prepare to launch into the deep science explorations. We will dissect the intricate data points that define 3I Atlas with greater precision, delving into the very mechanisms that drive its unique behavior and its unexpected volatility. We will examine its peculiar chemical signatures, its enigmatic trajectory, and its surprising activity levels, seeking to unravel the cosmic story it carries from another star. The journey into its profound secrets has only just begun, promising to reshape our view of the cosmos and our fundamental place within it. As the digital eyes of our instruments tracked the enigmatic 3I Atlas across the profound emptiness of the void, the true story of its journey began to unfold, not through direct visual inspection, but through the intricate, mathematical language of celestial mechanics. This interstellar visitor, designated 3I Atlas, unlike the familiar, gravitationally bound residents of our solar system, followed a trajectory that spoke volumes about its distant, alien origin far beyond the reach of our sun's gravitational dominion. You watch it trace a hyperbolic orbit, a path fundamentally distinct from the elliptical trajectories of planets, dwarf planets, and most comets that dutifully circle our sun, bound forever to its warmth. A hyperbolic trajectory signifies, unequivocally, that an object possesses an excess of kinetic energy relative to the gravitational pull of the sunday. It moves too swiftly, too powerfully, to ever be captured into a repeating, closed orbit. This means 3I Atlas is not a comet or asteroid that originated within our own cosmic neighborhood, residing in the distant Oort cloud or the main asteroid belt. Instead, it is merely passing through, a transient, uncatchable guest in our stellar home, a fleeting apparition in the cosmic theater. Its journey is a one-way passage, an open arc that will not return, destined to escape back into the vast, cold expanse between stars, carrying its secrets with it. This single, defining characteristic immediately sets it apart, unequivocally labeling it as a true voyager from another star system, a rogue ambassador from an unknown realm. The precise mechanics of its path through the solar system have been meticulously calculated and recalculated by an international consortium of astronomers, leveraging a global network of advanced telescopes and sophisticated computational models. One of the most critical measurements derived from these exhaustive observations is its orbital inclination relative to the ecliptic plane. This plane, a fundamental reference in solar system dynamics, marks the average orbital path of Earth and most other major planets in our solar system, which all lie roughly within a common, flattened cosmic disk, a remnant of the primordial nebula from which they formed. For 3I, Atlas, this inclination is measured at approximately 47 degrees. This represents a remarkably steep angle, almost halfway between the ecliptic and a path perpendicular to it, plunging diagonally through the familiar plane of planetary motion. Most solar system bodies, from planets to asteroids and even short-period comets, orbit much closer to this common plane, a direct consequence of their formation within that flattened, spinning protoplanetary disk. This significant tilt immediately sets 3I Atlas apart, hinting powerfully at its non-native status. It plunges into our system from an unusual, almost aggressive angle, cutting sharply across the familiar planetary traffic lanes, and then exits just as abruptly, a cosmic diver emerging from the depths of interstellar space. Such a highly inclined orbit is a compelling indicator of an object that formed elsewhere, ejected from a different stellar nursery, and now traverses the galactic plane with an independence rarely seen. Its closest approach to the Sun, known as its perihelion, occurred at a distance of about 1.1 AU. An astronomical unit, or AU, represents the average distance between the Earth and the Sun, a colossal span of approximately 150 million kilometers. So, 3I, Atlas, passed just slightly outside Earth's own average orbital path, placing it firmly within the inner solar system, where solar radiation is intense. This proximity, while not dangerously close in terms of collision risk, allowed for intense and sustained observational campaigns from both ground-based observatories and space-based telescopes, offering unprecedented detail. Crucially, while it was near enough for detailed study, it was not so near the Sun as to be dramatically heated to extreme destructive temperatures. This moderate perihelion distance plays a pivotal role in understanding its subsequent behavior, particularly concerning any potential outgassing. Many comets, when they approach the Sun, experience significant heating, causing their frozen volatiles, ices like water, carbon dioxide, and carbon monoxide to sublimate directly into gas. This process creates a glowing coma, a diffuse atmosphere of gas and dust, and often a spectacular tail, the very hallmarks of cometary activity. The relatively benign perihelion of 3I, Atlas, meant that any outgassing, if it occurred, would likely be less vigorous than that of a sun-grazing comet, yet still potentially detectable with modern instruments. The sheer speed of 3I, Atlas, is another defining characteristic, a testament to its interstellar origins and the powerful forces that propelled it. Its relative velocity on approach exceeded 55 kilometers per second. To put this incredible speed into a more relatable perspective, imagine a journey across a vast continent, say, from Lisbon on the Atlantic coast of Europe to Vladivostok on the Pacific coast of Asia, a distance of approximately 10,000 kilometers. This object travels faster than any human-made spacecraft, including the fastest probes like NASA's Parker Solar Probe at its perihelion, which, while faster relative to the Sun, still originates from within our system. 3I, Atlas, moves at a speed that would carry it from New York to Los Angeles, a distance of nearly 4,000 kilometers, in under 90 seconds. Such incredible velocity is a hallmark of interstellar objects, providing irrefutable evidence that 3I, Atlas, arrived from beyond the gravitational influence of our Sun, having gained its tremendous momentum from another star system, or perhaps from the chaotic gravitational dance within a dense stellar cluster. It carries the residual energy of its violent ejection from its distant home, perhaps flung out during a close gravitational encounter with a massive giant planet, or even a binary star system. This tremendous speed, far exceeding the escape velocity of our own Sun, dictates the brevity of its visit, offering only a fleeting glimpse of its nature before it disappears back into the cosmic currents. Its trajectory unfolded with an almost unnerving precision, a path seemingly etched with cosmic inevitability, devoid of any discernible deviation. It moved as if slipping through a barely perceptible doorway open between stars, an invisible portal guiding its precise passage, leaving the solar system as swiftly and silently as it entered. This rapid transit inherently highlights the immense challenge of observing such objects with adequate detail. The window for study is inherently time-bound, closing quickly as the visitor recedes into the interstellar medium, becoming progressively fainter, colder, and more distant with each passing moment. Astronomers must act with unparalleled urgency, coordinating global resources and advanced instrumentation to maximize data acquisition during this brief window. Every precious hour of observation yields invaluable information. A brief, one-sided conversation with a silent, enigmatic traveler from beyond. One of the most profound and perplexing observations concerning 3I, Atlas, revolves around its non-gravitational accelerations. For typical comets, particularly those making their first pass through the inner solar system, the intense solar radiation causes their frozen volatiles, primarily water ice, carbon dioxide, and carbon monoxide, to sublimate directly from solid to gas. The expulsion of these gases and entrained dust particles acts like tiny, continuous rocket-like thrusts. These subtle forces subtly alter their paths, causing measurable deviations from purely gravitational trajectories, much like a small thruster nudging a spacecraft off its predicted course. Yet, for 3I, Atlas, these non-gravitational accelerations appear remarkably negligible, almost entirely absent. This presents a significant academic tension, directly challenging long-held expectations of comet-like behavior for interstellar visitors, especially given the precedent of the first recognized object of this class. The initial interstellar object, Oumuamua, famously exhibited a small but definite non-gravitational acceleration, which was ultimately attributed to outgassing, albeit of an unusual kind, prompting intense scientific debate about its composition and nature. However, 3I, Atlas, appears to defy this expectation, presenting a stark contrast. One comprehensive study, meticulously analyzing over 4,000 astrometric observations gathered from a diverse array of telescopes worldwide, placed an extremely low upper limit on any such acceleration, 15 meters per day squared. To grasp the profound significance of this value, consider the extraordinary precision involved in detecting such minute deviations over vast distances and extended periods. This measurement represents the absolute maximum deviation from a purely gravitational path that could possibly exist, given the observed data and the inherent uncertainties of astronomical measurement. It is an incredibly small value, orders of magnitude below what would be expected from a typical active comet, even one with a relatively small nucleus. This suggests an object that is either largely devoid of volatiles, making it more akin to a rocky asteroid, or one whose surface is unusually inert and resistant to sublimation, or perhaps even one with a remarkably resilient, protective crust that effectively seals in any interior ice, preventing its escape and the creation of a visible coma or tail. The implication is profound. 3I, Atlas, is not behaving like a typical comet, despite the prevailing hypothesis that most ejected interstellar objects would be icy, due to the vast reservoirs of cometary material in exoplanetary systems. It does not appear to be shedding material in any significant, detectable way, presenting a cosmic enigma. This near-total absence of non-gravitational forces is a truly quirky detail, a silent anomaly in the grand, dynamic ballet of the cosmos. It implies 3I. Atlas is not behaving like a typical comet, defying the very definition of these icy wanderers that traditionally announce their presence with a luminous display. It does not appear to be shedding material in any significant way, unlike the familiar celestial fireworks of Halley's Comet, or the more recent, widely observed comet Neowise. Imagine trying to track a vast, silent ship across a perfectly calm ocean. Its movement almost entirely dictated by the deep, unseen currents of gravity, not by any internal propulsion or the subtle expulsion of steam from its hull. This is how 3I, Atlas, seems to navigate the cosmos. A ghost ship propelled only by the universal pull of mass, offering no visible exhaust. What does this quiet, unreactive journey imply about its fundamental composition or the nature of its surface? Could it be a purely rocky body, like an asteroid, a fragment of a shattered exoplanet, rather than an icy comet from an Oort cloud analog? Or perhaps it possesses a remarkably resilient protective crust, a thick layer of refractory material that effectively seals in its interior volatiles, preventing them from escaping and creating a visible tail even under solar heating. This profound lack of detectable outgassing raises fundamental questions for planetary science and our understanding of exoplanetary systems. Is 3I, Atlas, indeed an interstellar asteroid, a solid fragment of a rocky planet from another star system, similar to what we find in our own asteroid belt? Or is it an entirely new, unforeseen class of object, one that defies our current classifications and challenges our established models of interstellar object populations? The implications are far-reaching for our understanding of planetary formation processes beyond our Sun, suggesting a greater diversity of ejected material than previously assumed. If it is indeed a predominantly rocky body, it would represent a significant departure from the cometary nature of the first recognized interstellar visitor, Oumuamua, which, despite its unusual shape, eventually showed signs consistent with outgassing. The scientific community grapples intensely with these competing possibilities, each scenario opening new and exciting avenues of inquiry into the diversity and evolution of exoplanetary systems. What forces truly shaped this visitor's path, and what secrets are locked within its silent, unyielding exterior? Could such an object simply be a cosmic wanderer, devoid of the familiar icy breath of comets, a silent messenger from an unknown, perhaps ancient world? Its stoic journey offers a compelling mystery. Its meticulously plotted trajectory suggests it will continue its outward journey, steadily receding from our Sunday. It will cross beyond Earth's orbit in the coming months, then beyond Mars, and eventually beyond the gas giants, before disappearing into the deep interstellar void. This offers a rare, yet inherently time-bound, window of study for Earth-based and space-based telescopes, a race against time for astronomers. As it departs, its distance from the Sun increases steadily, making it progressively fainter, colder, and significantly harder to observe, its reflected light dimming against the vast backdrop of distant stars. The focus of astronomical inquiry, therefore, shifts from merely tracking its precise path to gleaning every last bit of information about its physical nature, its rotation, its surface properties, and its potential composition. What final, crucial secrets might its fading light still reveal about its origins or its constitution, before it becomes too faint to discern, a mere ghost among the nebulae? The meticulous tracking and analysis of 3I, Atlas, therefore, is not merely about plotting a path through the cosmic ocean. It is about decoding a profound message from another star system, a silent communique carried across light years, offering a tangible piece of another stellar realm. It is about understanding the fundamental properties of a visitor that, in its very silence and resistance to traditional classification, refuses to conform to our expectations, pushing the boundaries of our cosmic understanding. The brief but impactful journey of 3I, Atlas, through our solar system has already reshaped some of our deepest assumptions about interstellar objects and the variety of material exchanged between star systems. Its precise orbital characteristics and the puzzling lack of activity compel us to look closer, to question further, to imagine more, as its silent passage continues into the unknown, leaving behind a trail of scientific intrigue and unanswered questions. The next phase of understanding this enigma will require us to probe its very essence. From the intricate dance of its orbital trajectory, you now delve deeper, seeking the very essence of 3I, Atlas. Its path through our solar system, however unique, reveals only a fraction of its cosmic tale. The profound narrative unfolds within its spectral fingerprint, a chemical signature etched in light and broadcast across the vastness of space. Astronomers worldwide, leveraging an array of sophisticated instruments, meticulously analyze the light scattered and emitted by the object's expansive coma. This ephemeral, hazy envelope, continually formed by the sublimation of ices from the nucleus, functions as a dynamic cosmic laboratory. It meticulously reveals the fundamental building blocks of this enigmatic interstellar visitor. You observe the raw data, spectrum by intricate spectrum, each line and dip telling a story of atomic and molecular presence. These spectral patterns are akin to a unique barcode, identifying the specific volatile compounds present. Acquiring these spectra requires immense observational power. Ground-based telescopes, equipped with high-resolution spectrographs, target specific emission lines. They detect photons emitted as molecules fluoresce under solar radiation. Space-based observatories, crucially, overcome Earth's atmospheric absorption, particularly for vital infrared wavelengths, where many key volatiles radiate their unique signatures. The direct detection of CO₂, for instance, is often masked by terrestrial carbon dioxide, necessitating space-based platforms like JWST for unambiguous identification. The most striking and perplexing revelation emerges from 3I, Atlas's volatile inventory. The coma consistently displays an unusually high ratio of carbon dioxide to water. Precise measurements, derived from the relative strengths of their characteristic spectral lines, indicate this ratio to be approximately 8:1. This means the object's outgassing material contains 8 times more carbon dioxide than water ice. A profound and unprecedented departure from typical cometary compositions. This figure stands as the largest CO₂-H2O ratio ever definitively observed in any comet-class object. For critical context, most comets originating from our own solar system, particularly those from the Jupiter family or the Oort cloud, exhibit a water-dominant coma. Their CO₂ fractions rarely exceed 20% relative to water, often much less. Even the interstellar comet Borisov, observed in 2019, showed a composition broadly consistent with solar system comets, primarily water-rich, with only minor CO₂ contributions. This stark reversal of expected ratios immediately ignites intense academic tension within the scientific community. The prevailing astrophysical models for comet formation, especially those within a solar nebula like our own, struggle significantly to account for such an overwhelmingly CO₂-rich composition, prompting a re-evaluation of fundamental assumptions about protoplanetary disk chemistry and planetesimal accretion. What cosmic conditions could have forged such an anomalous object? Scientists are now engaged in vigorous debate regarding the profound implications of this volatile mix. Does this extreme CO₂ dominance unequivocally suggest its formation in an exceptionally cold, distant region of its home star system. Perhaps it originated within a dense, cold molecular cloud far removed from any star's initial warmth, where such highly volatile compounds could condense and remain stable. The condensation temperatures for CO₂ are significantly lower, around 80 Kelvin, compared to water ice at approximately 200 Kelvin. This extreme cold would allow carbon dioxide to become a primary constituent rather than a secondary or trace element. The formation of comets in these frigid environments, potentially within the outer reaches of a protoplanetary disk or even directly from the interstellar medium, could explain this unusual chemical signature. Alternatively, could it have formed in a different type of stellar nursery altogether, one with a distinct chemical environment and different initial conditions, perhaps enriched in carbon and depleted in oxygen? The presence of so much carbon dioxide, a volatile that sublimes at much lower temperatures than water ice, strongly points toward a deeply preserved, pristine sample of interstellar material. It is as if the ingredients of an ancient recipe have been preserved and now released, the material seeming foreign yet remarkably familiar, a relic from another cosmic kitchen, offering profound clues to galactic diversity and chemical evolution. Beyond its gaseous exhalations, the solid nucleus of 3I, Atlas, also presents several intriguing physical characteristics. Its albedo, a crucial measure of its surface reflectivity, remains remarkably low. Observations consistently indicate an albedo of around 0.04. This means the object reflects only 4% of incident sunlight, making its surface significantly darker than fresh asphalt or even charcoal. Such low reflectivity is a common trait among cometary nuclei, which are often coated in a complex layer of organic refractory materials, sometimes called tholins or amorphous carbon. These dark materials are thought to be formed by the irradiation of simpler organics, by solar ultraviolet light and cosmic rays, creating a dark protective crust. This dark, non-reflective surface efficiently absorbs most of the incoming solar radiation, serving as the primary energy source driving the sublimation process. This absorption causes the surface to heat, triggering the release of volatiles. However, the specific combination of this low albedo with other observed factors, particularly its thermal response and extreme CO₂ ratio, creates a complex and challenging puzzle for researchers, suggesting a unique surface composition and possibly a unique evolutionary history that preserved its dark mantle over vast interstellar distances. Furthermore, its thermal inertia appears surprisingly subdued for an object of its presumed age, and its recent, relatively close approach to the Sunday. Thermal inertia quantifies a material's resistance to changes in temperature, essentially how quickly its surface temperature responds to heating or cooling. It reflects both thermal conductivity and heat capacity. For 3I, Atlas, this value is estimated to be approximately 10 Jm to the power of -2, K to the power of -1, S to the power of -1, CAT squared. This figure is significantly lower than typical values measured for even highly porous asteroids or many cometary nuclei, which often range from 50 to 200 Jm to the power of -2K to the power of -1 S to the power of -1 squared. This subdued thermal inertia suggests a highly porous, loosely consolidated surface layer that heats and cools with remarkable rapidity. To illustrate, imagine the difference between a block of styrofoam and a dense granite rock. The styrofoam possesses a much lower thermal inertia because heat does not conduct well through its many air pockets. This characteristic implies that heat does not penetrate deeply or efficiently into the object's interior. This shallow heat penetration directly impacts how and where volatiles are released from the nucleus, potentially leading to episodic bursts of activity rather than sustained outgassing, and preserving deeper ice layers from complete sublimation. This property is crucial for accurately modeling its observed activity. The profound implications of these combined findings continue to resonate throughout the astronomical community. The unusual volatile inventory, particularly the overwhelming CO2 dominance, hints strongly at a formation in a distant, colder star system environment. Such an environment might be found within the outer reaches of a protoplanetary disk, where temperatures are low enough for CO2 to condense, or perhaps even in a dense, cold molecular cloud, far from any star's initial warmth. This extreme cold would have allowed highly volatile compounds like carbon dioxide to condense and remain stable as primary constituents, rather than existing merely as secondary or trace elements. Could this object truly represent a direct, pristine sample of primordial interstellar dust and gas, largely untouched by significant stellar processing or the intense radiation of a young star? This question fundamentally challenges our understanding of cosmic chemistry and the diversity of planetesimal formation across the galaxy. The existence of such an object forces a re-evaluation of how planetary building blocks form in different stellar environments, expanding the known chemical diversity of the universe. The high CO2 content also raises critical questions about the potential for cryovolcanism, or more explosive outgassing events. Carbon dioxide ice, when heated, converts directly into gas, expanding dramatically. If substantial pockets of CO2 ice are trapped beneath a less volatile crust, perhaps composed of water ice or refractory organics, sudden exposure to even slight solar warming could trigger rapid expansion. This rapid expansion might lead to localized bursts, ejecting significant amounts of material into space, similar to a pressure cooker releasing steam. Such events could readily contribute to the rapid and often puzzling changes observed in 3I, Atlas, phenomena that have intrigued and baffled astronomers since its initial discovery. You ponder the immense forces at play, the delicate, explosive balance between internal pressure and the absolute vacuum of space. How might these internal dynamics be influencing its erratic behavior and its sudden brightening events? Could this internal pressure mechanism be responsible for its observed non-gravitational accelerations, creating a self-propelling effect? What does such an exotic composition tell us about the broader galactic neighborhood from which 3I Atlas originates? If objects possessing such extreme volatile ratios are indeed common, they could play a pivotal role in transporting significant amounts of complex organic molecules and crucial volatiles across vast interstellar distances. This has profound implications for the origins of life itself, suggesting that the fundamental building blocks might be widely distributed throughout the galaxy. They could be effectively delivered to nascent planetary systems by such cosmic wanderers. It is a quirky detail, almost poetic, that a seemingly simple chemical ratio could hold such profound universal significance, linking distant star systems to our own, and potentially seeding new worlds with the ingredients for life. This perspective expands our view of galactic interconnectedness, making 3I Atlas a messenger from the wider cosmos, carrying secrets from beyond our stellar home. The data continues to accumulate, enhancing our understanding. Ground-based telescopes, equipped with cutting-edge, high-resolution spectrographs, meticulously track the faint emissions emanating from 3I Atlas. Instruments like those on the Very Large Telescope, VLT, in Chile, or the Keck Observatory in Hawaii, provide critical insights, particularly by observing the forbidden oxygen lines that indicate water dissociation and the emissions from simple carbon-bearing molecules like CN and C2. Furthermore, the James Webb Space Telescope, JWST, with its unparalleled infrared sensitivity, offers crucial insights into the precise molecular species present. Its NIRSpec and MIRI instruments distinguish between various carbon-bearing compounds, water isotopes, and other trace gases with exquisite detail, including the direct detection of CO₂ at 4.26 micrometers. Each photon captured adds another brushstroke to the increasingly intricate portrait of this interstellar interloper. The remarkable consistency of these spectral signatures across multiple observations from different observatories and at varying wavelengths significantly strengthens the conclusions drawn about its unique composition, minimizing observational biases and confirming its exotic nature. The subdued thermal inertia, when coupled with the exceptionally low albedo, suggests a surface that is not only profoundly dark but also highly insulating. This unique combination implies that the outer layers of 3I, Atlas, are either extremely fluffy or composed of loosely aggregated dust grains with a substantial amount of void space, possibly a result of its formation process in a low-gravity environment, leading to a very fragile structure. Such an open, porous structure would profoundly facilitate the rapid outgassing of volatiles. Solar radiation would penetrate only the very uppermost layers, preventing heat from efficiently conducting deeper into the nucleus. This mechanism allows for swift surface heating and cooling, which directly influences the observed activity. This contrasts sharply with denser, more consolidated cometary bodies found within our own solar system, where heat can penetrate deeper and trigger more sustained, rather than episodic, outgassing, thereby altering their thermal evolution differently. The rapid thermal response also means that any changes in solar illumination quickly translate into changes in activity, making its behavior highly sensitive to its environment. The central question persists. Weaving through every scientific discussion, are these extreme observations entirely consistent with a natural, albeit exceptionally rare, interstellar object? Or do they subtly hint at something more unconventional, perhaps even something manufactured, given the peculiar combination of traits? The overwhelming CO₂ dominance, the remarkably low albedo, and the peculiar thermal response together paint a picture of an object fundamentally unlike any other seen in such detail. The global scientific community grapples with these profound anomalies, constantly refining theoretical models and diligently seeking new, comprehensive explanations. Researchers explore scenarios ranging from an object formed in a uniquely cold and carbon-rich region of space to one that has undergone unusual processing, such as intense radiation exposure in its home system, or even an exotic type of cryovolcanic activity triggered by internal stresses. Some theories even consider whether the object might be a fragment of a larger, highly differentiated body. Each new piece of observational data, each nuanced interpretation, adds further complex layers to the enduring mystery surrounding 3I, Atlas, deepening the scientific intrigue and pushing the boundaries of astrophysical understanding. As you continue to dissect the chemical heart of this interstellar enigma, its physical form remains largely a mysterious silhouette. Our next focus will shift from its intrinsic composition to its tangible presence, its precise size, its discernible shape, and the subtle, rhythmic patterns of its rotation. The celestial ballet of light and shadow, observed through the distant gaze of our instruments, now yields to a deeper inquiry. We turn our attention from its dynamic, ephemeral behavior to the very physical essence of 3I, Atlas itself, seeking to comprehend its fundamental dimensions and internal mechanics. You sense the true, yet elusive, scale of this interstellar wanderer. Its nucleus, the solid heart of the object, is shrouded in an expansive, obscuring coma of dust and gas. This presents a formidable challenge to direct, high-resolution imaging, making its precise size a matter of careful inference. Through a combination of observations, primarily measuring its brightness in reflected sunlight and its thermal emission, astronomers constrain its potential diameter. The nucleus of 3I, Atlas, is estimated to be somewhere between 0.32 kilometers and 5.6 kilometers in diameter. This range is vast, spanning from a modest 320 meters, roughly the length of 3 standard football fields laid end to end, to a substantial 5,600 meters, a size comparable to a small mountain range, or the entire width of a modest urban district. This significant uncertainty, a factor of nearly 20, reflects the inherent difficulty of peering through its dense, dusty veil and the critical role of unknown parameters. Estimations of cometary nuclei size often rely heavily on assumptions about the object's albedo, or how reflective its surface might be. A darker, less reflective surface, absorbing more sunlight, would imply a significantly larger object to account for the observed brightness from reflected light. Conversely, a brighter, more icy surface would suggest a smaller nucleus. The exact albedo of 3I, Atlas, remains unknown, contributing directly to this wide diameter range. For comparison, the nucleus of Halley's comet is about 15 kilometers long, while the first interstellar object, Oumuamua, was estimated to be only a few hundred meters in its longest dimension. Without a direct high-resolution image, which current ground-based and space-based technology cannot yet achieve for such a distant, small, and rapidly moving object, its precise dimensions remain a calculated inference. This is a fundamental piece of the puzzle still in flux, with profound implications. The difference between a 320-meter object and a 5.6-kilometer behemoth carries significant consequences for its total mass, its internal structure, and its ability to retain volatiles over cosmic timescales. A larger nucleus provides more surface area for outgassing, but also a larger heat reservoir. A smaller nucleus would be more sensitive to solar heating, potentially leading to more rapid sublimation. Researchers use complex thermal models, considering the object's distance from the Sun and its assumed composition, to refine these size estimates. But the albedo remains the primary unknown. Rotation period measurements for 3I, Atlas, remain deeply uncertain, a testament to the persistent observational hurdles. Direct optical resolution of such a distant, small nucleus is nearly impossible with current telescopes. Even instruments like the Hubble Space Telescope struggle to resolve such fine details. Instead, scientists infer its spin from indirect evidence, primarily the morphology and symmetry of its expansive dust coma and tail. The observed symmetrical outflow of dust and gas, as seen in images from various observatories, offers a crucial clue. This symmetrical distribution suggests a relatively slow, deliberate rotation. Initial estimates, derived from the stable appearance of the coma over several observation windows, place this spin on the order of 10 to 20 hours. Imagine a vast, ethereal top, turning slowly through the cosmic void, its rotation subtly shaping the distribution of ejected material into a somewhat uniform envelope. A faster spin, for instance, a period of only a few hours, might create a more elongated or asymmetric coma, or even cause the nucleus to shed material unevenly due to centrifugal forces. Such rapid rotation could also lead to rotational breakup if the object's internal strength is insufficient. The precise rotational state influences how volatiles escape from the surface, how active regions are exposed to solar radiation, and ultimately how the nucleus evolves over time. If the rotation were significantly faster, centrifugal forces could potentially overcome the object's internal gravity, leading to fragmentation or reshaping, a phenomenon observed in some solar system comets. The slow spin, therefore, implies a certain degree of stability, allowing the object to retain its structure even while actively outgassing. This rotational period, if confirmed, would place 3I, Atlas, within the typical range for many comets in our own solar system, such as Comet 67P, Churyumov-Gerasimenko, which has a period of about 12.4 hours. This suggests that despite its interstellar origin, familiar physical processes of sublimation and rotation might be at play. However, the absence of a clear periodic light curve, which typically reveals rotational periods through regular brightness variations as an irregularly shaped nucleus spins, complicates these measurements. This absence might be due to a lack of significant shape irregularities on the nucleus, or simply the overwhelming brightness of the coma, masking any nuclear variations. As if a pebble tossed across a vast pond, this object bears imprints of forces both gentle and immense, its true form obscured by the very activity that defines it. This persistent shroud of ejected material, a dynamic cocoon of dust and gas, makes direct imaging of its nucleus impossible, transforming its study into a cosmic game of hide and seek. The nucleus remains perpetually veiled, a ghost in its own brilliant light. Academic tension builds significantly when we consider the mass of 3I, Atlas, a parameter derived indirectly but with profound implications. One detailed analysis, meticulously accounting for its weak yet detectable non-gravitational acceleration, indicates a minimum mass of approximately 3.3 times 10 to the power of 10 tons. This colossal figure, equivalent to 33 billion metric tons, speaks to the substantial nature of 3I, Atlas. Non-gravitational acceleration refers to the subtle, persistent deviations from a purely gravitational orbit, deviations that cannot be explained by the gravitational tugs of the Sun and planets alone. These slight pushes or pulls arise from the outgassing of volatiles, essentially acting as tiny rocket-like thrusts from escaping gases. As material sublimes from the nucleus and streams into space, it imparts a reaction force, much like a rocket engine. A larger mass would require more significant outgassing to produce the same observed acceleration, as inertia is greater and resists changes in motion. Conversely, a smaller mass would be more easily perturbed by a given thrust. The presence of non-gravitational forces unequivocally confirms active sublimation, a hallmark of cometary behavior, but quantifying its effect to precisely determine mass is fraught with complexity. It requires precise models of gas ejection velocities, directions, and the distribution of active regions across the nucleus. Is the outgassing uniform across the surface, or concentrated in powerful, asymmetric jets? Are the jets constant, or do they vary with the rotation of the nucleus and its exposure to sunlight? These questions directly impact the accuracy of mass calculations, leading to ongoing scientific debate and refinement. The inferred minimum mass is critical. It informs our understanding of its internal composition and structural integrity. An object of this mass, even at the lower end of the diameter, estimate 32 kilometers, would imply an extraordinarily high density, far exceeding that of typical porous cometary ice. This would suggest a substantial rocky or metallic component, or an incredibly compact, non-porous structure. This density paradox fuels intense discussion among researchers. The precise shape of 3I, Atlas, remains hidden beneath its cocoon of dust. It is like trying to discern the exact form of a small boat caught in a dense, swirling fog on a moonless night, where only vague outlines are visible. What hidden features truly lie beneath this persistent veil? Could it be a simple spheroid, a smooth, undifferentiated body, perhaps shaped by eons of gentle erosion, or perhaps a more complex, elongated, or even bilobed structure, reminiscent of the contact binary comets like 67P, Churyumov-Gerasimenko, which appears like two distinct lobes joined together. Such an irregular form would profoundly influence its spin dynamics, its thermal evolution, and how material is shed from its surface, creating uneven jets and tails. The internal structure, too, remains a profound mystery. Is it a loosely aggregated rubble pile, a collection of smaller fragments held together by weak gravity, vulnerable to disruption, or a more consolidated, monolithic body, formed under immense pressure in its home system? These details are not mere curiosities. They are crucial for understanding its formation history in a distant star system and its resilience across vast interstellar distances. What clues might be hidden within its unseen topography, waiting to be revealed by future, more advanced instruments? The interplay between the inferred size, the uncertain rotation, and the calculated minimum mass creates a fascinating, yet challenging picture. If the nucleus is at the smaller end of its estimated diameter, 0.32 kilometers, but possesses the minimum mass, 3.3 times 10 to the power of 10 tons, its bulk density would be astonishingly high, perhaps exceeding 50,000 kilograms per cubic meter. This value is far greater than that of typical cometary ice, which is usually less than 1,000 kilograms per cubic meter, and even denser than solid rock or iron. This density paradox would imply a substantial rocky or metallic core, or an incredibly compact, non-porous structure. Conversely, if it is at the larger end, 5.6 kilometers, with the same mass, its density would be much lower, more consistent with a porous, icy body, similar to many solar system comets. This wide range of possibilities fuels significant academic tension and vigorous debate. Researchers grapple with these constraints, attempting to reconcile them with existing models of interstellar object formation and evolution. The precise mechanism behind its non-gravitational acceleration remains a key uncertainty. Is it driven primarily by water ice, sublimating at relatively warm temperatures closer to the Sun, or by more exotic supervolatile compounds like carbon monoxide or carbon dioxide, 212, which sublimate at much colder temperatures, far from the Sun? The composition of these escaping gases directly influences the thrust generated, and consequently, the accuracy of the mass determination. Different volatiles have different molecular weights and ejection velocities, leading to varying specific impulses. If CO or CO2 are significant drivers, the non-gravitational forces could be substantial, even with modest outgassing, potentially leading to a lower mass estimate. This adds another layer of complexity to the calculation. The very act of observing 3I, Atlas, pushes the limits of astronomical instrumentation and theoretical modeling. Could a complex interaction of outgassing jets and an irregular shape create the observed coma symmetry, even with a more complex or faster spin that is currently masked? The possibility of an anisotropic outgassing, where gases escape preferentially from certain areas, could mimic a slower, more uniform rotation, further obscuring the true dynamics. The challenges in determining these fundamental parameters are immense, compounded by the fleeting nature of interstellar visitors. Unlike objects within our solar system, which can sometimes be visited by probes or observed repeatedly over decades, interstellar visitors like 3I, Atlas, offer only brief, transient opportunities. Its rapid transit through our system means that every observation is precious, every data point a hard-won victory against the vastness of distance and the relentless march of time. The lack of a clear light curve, which typically reveals rotational periods through periodic brightness variations as an irregularly shaped nucleus spins, further complicates matters. This absence might be due to a lack of significant shape irregularities on the nucleus itself, or simply the overwhelming brightness of the coma, masking any nuclear variations that might otherwise be detectable. The dust and gas cocoon, while aesthetically beautiful and a sign of activity, acts as a profound obscuring agent, preventing direct observation of the nucleus. Understanding the object's torque, the force that causes or changes rotation, is also critical for a complete picture. Non-gravitational forces, if asymmetric in their application, could exert a significant torque on the nucleus, potentially altering the object's spin state over time. This could explain some of the observed rapid changes in its activity, as new active regions are exposed or old ones become quiescent due to changes in orientation. Does 3I Atlas possess a stable, primordial spin, largely unchanged since its ejection from a distant star system? Or has its long journey through interstellar space and its recent passage through our solar system significantly altered its rotational dynamics? These questions are at the heart of understanding its long-term evolution and its origins in a distant stellar system. Future instruments, such as the James Webb Space Telescope, with its infrared capabilities, or next-generation extremely large ground-based telescopes, hold the promise of perhaps piercing through some of this dust, offering tantalizing glimpses of the nucleus itself. Such observations could revolutionize our understanding of its true size, shape, and rotational state. Unraveling these intricate physical characteristics demands ever more refined observational techniques and sophisticated analytical models, a journey we continue to pursue with unwavering dedication, pushing the boundaries of what we can discern about these enigmatic cosmic travelers. The subtle non-gravitational influences detected on 3I Atlas, suggesting a volatile release or perhaps a more complex interaction, compel us to scrutinize the very tools that reveal such faint signatures. You watch as the narrative of this enigmatic object expands to encompass the sophisticated instruments and inherent uncertainties defining modern astrophysics. Understanding 3I Atlas requires not just keen observation, but a deep appreciation for the delicate dance between light and sensor. Astronomers employ a formidable array of telescopic assets to capture the fleeting details of objects like 3I Atlas, the James Webb Space Telescope's near-infrared spectrograph, or NIRSpec, for instance, became a crucial eye. It achieved signal-to-noise ratios of approximately 15 at 2.5 micrometers, a remarkable feat for such a distant, dim target. This clarity permitted the discernment of specific molecular absorption bands, hinting at the object's chemical composition. Meanwhile, the venerable Hubble Space Telescope, with its wide-field camera 3, delivered angular resolution near 0.05 arcseconds in visible bands. This precision allowed for detailed astrometry, tracking the object's position against background stars with exquisite accuracy. Ground-based observatories, often working in concert, provided an invaluable temporal dimension. They delivered cadence exposures every 10 minutes, generating light curves that revealed subtle changes in brightness and rotation. Each instrument, a specialized ear, strained to catch a cosmic whisper. Yet, collecting data is only half the challenge. Interpreting it is the other. Scientists face a constant battle against numerous sources of error and noise. Calibration drift, for example, is a persistent concern. The sensitivity of instruments can subtly change over time due to thermal fluctuations or radiation exposure. Correcting for this requires meticulous recalibration against known stellar standards, a process that can introduce its own set of minor discrepancies. Parallax corrections are also critical for an object moving across the sky. As Earth orbits the Sun, our vantage point shifts, causing foreground objects to appear to move relative to more distant background stars. Precisely accounting for this apparent motion is essential for determining an accurate trajectory for 3I Atlas, especially when trying to differentiate true motion from observational artifact. Perhaps one of the most demanding tasks involves faint tail retrieval against a bright sky background. The coma and tail of 3I Atlas, composed of diffuse gas and dust, scatter sunlight, making them extremely faint. Distinguishing this ethereal glow from the zodiacal light, or even scattered moonlight in ground observations, demands sophisticated image processing algorithms and careful background subtraction. It is like attempting to discern a specific musical note during a distant thunderstorm, requiring immense computational power and human discernment. The academic tension arises not just from the raw data, but from the error envelopes that surround every measurement. How confidently can scientists claim CO₂ dominance in the volatile composition of 3I Atlas, when uncertainty margins remain at plus or minus 30% in some spectral bands? Similarly, establishing precise size limits for the nucleus becomes a complex endeavor when the observed brightness can be influenced by varying albedo or even transient outgassing events. The very detection of non-gravitational effects, so central to understanding 3I Atlas's anomalous trajectory, relies on exquisitely precise astrometric measurements where even minute errors can skew the interpretation. Every data point arrives with its own probabilistic cloud. Consider the precision required for these observations. A single pixel on the JWST's near-spec array might cover only a few tens of milliarc seconds. Yet within that tiny spatial extent, the instrument must differentiate subtle spectral features. The angular resolution of Hubble, near 0.05 arc-seconds, translates to resolving features roughly the size of a small car on the Moon's surface, if such a car were visible from Earth. This level of detail is necessary to distinguish the nucleus from its surrounding coma. Ground observatories, despite atmospheric blurring, compensate by providing rapid cadence exposures every 10 minutes, allowing for the creation of time series data. This rapid sampling helps to average out atmospheric distortions and capture short-lived events like outburst flares. A quirky detail in this pursuit involves the sheer volume of dark frames collected. These are exposures taken with the telescope shutter closed, measuring the intrinsic electronic noise of the detector. Thousands of these frames are averaged and subtracted from science images to remove this background hum, ensuring that only light from the cosmos remains. This constant self-auditing ensures data integrity. Yet, despite these meticulous efforts, the scientific community often finds itself in vigorous debate. The persistent challenge lies within the error envelopes. How confidently can one assert CO₂ dominance or precise size limits when uncertainty margins sometimes approach 30%? These margins become the battleground for competing hypotheses. You understand that every scientific claim, every published paper, is ultimately a statement of probability. The error bars are not merely technical footnotes. They are the very boundaries of current understanding, delineating what is known with high confidence from what remains speculative. Pushing these boundaries requires not just more powerful telescopes, but also innovative data analysis techniques and a willingness to confront ambiguity. The story of 3I Atlas is thus also a story of human ingenuity grappling with cosmic uncertainty. We press on now to compare 3I Atlas with other known populations, seeking context in the vast cosmic tapestry. Even with our most refined instruments, the universe often reveals itself in fragments. A truth brought into sharp focus when considering 3I Atlas. Within the vast, unseen tapestry of interstellar visitors, you watch the sky, but what passes unnoticed through the dark? Astronomers estimate a flux rate of approximately 0.1 to 1 interstellar object per year passing through the inner solar system. This means, on average, a cosmic wanderer might arrive every 1 to 10 years. These are not local residents, but travelers from beyond our star's gravitational dominion, carrying secrets of distant stellar nurseries. However, our current observational reach is inherently incomplete. Sky coverage for dedicated surveys remains around 70%. This leaves a substantial portion of the celestial sphere unmonitored at any given moment, a blind spot where countless objects could silently traverse. Detection biases further skew our understanding. Telescopes are designed to capture light, and fainter objects are harder to discern. Our survey nets predominantly favor objects brighter than magnitude 19. An object at magnitude 19 is roughly 250,000 times fainter than a star visible to the naked eye. This means smaller, darker, or more distant interstellar objects are systematically overlooked, vanishing into the background noise of the cosmos. Imagine a vast, deep ocean stretching beyond all known horizons. You cast a net, designed to catch only the largest and brightest fish. This is how our current interstellar object surveys operate. We glimpse rare, luminous specimens, but the true diversity and abundance of smaller, darker forms remain largely unknown. This creates a significant academic tension. The very existence of 3I Atlas, with its apparent substantial size and mass, challenges established population models. Current theories on mass ejection from forming planetary systems suggest a prevalence of smaller, kilometer-scale fragments, or even meter-sized debris, rather than objects many kilometers across. Yet, 3I Atlas appears far larger and more massive than these models predict for typical interstellar visitors. If our survey net catches only the largest visitors, are we missing countless smaller ones, perhaps millions of them, which could paint a different picture of galactic transport? The implications are profound. If 3I Atlas represents a common class of interstellar objects, then our understanding of how stars shed their nascent material, or how interstellar reservoirs are populated, might require significant revision. Perhaps the processes of planet formation are far more violent, ejecting larger chunks of matter than previously assumed. Or perhaps the interstellar medium itself harbors a greater density of substantial objects than our models currently account for. The very rarity of detections, coupled with the anomalous nature of 3I Atlas, fuels this debate. Consider the orbital velocities involved. Typical interstellar objects might travel at speeds exceeding 20 kilometers per second relative to the Sunday. This velocity, combined with the limited sky coverage, makes detection a challenge, akin to spotting a specific grain of sand on a vast, windswept beach during a fleeting moment. A quirky detail emerged during one survey's early phases. A software glitch initially filtered out many faint, fast-moving streaks as instrument noise, inadvertently discarding potential ISO candidates before human review. It took months to correct, highlighting the subtle ways biases can embed themselves. The sheer volume of space is staggering. Even with 70% sky coverage, the remaining 30% represents an immense, unobserved volume, equivalent to millions of cubic astronomical units. Within this unseen expanse, what unseen traffic might traverse the dark? What silent voyagers perhaps only tens of meters across, slip through our observational gaps, never to be recorded. The universe does not wait for our telescopes to point. It simply moves. This uncertainty around population statistics directly impacts our understanding of galactic dynamics. Are these objects primarily ejected from active star-forming regions, or are they relics from older, more stable systems? The mass distribution of interstellar objects offers a critical clue to their origins. If 3I Atlas is an outlier, it might be a statistical anomaly. If it is representative, then our entire framework for interstellar transport needs re-evaluation. The academic tension is palpable. Are our models flawed, or is 3I Atlas simply a truly exceptional visitor? The answer holds keys to understanding stellar evolution and the very fabric of the galaxy. We must next turn our gaze to the theoretical underpinnings of these journeys, exploring the formation pathways and transport models that might bring such objects from distant star systems to our own. The previous discussions about 3I Atlas, its enigmatic changes, and its swift, silent passage through our system invariably lead to one fundamental inquiry. You ponder not just its present trajectory, but the profound, almost haunting question of its origins. How did such an object, a cosmic wanderer carrying echoes of a distant, unknown star, arrive here from the depths of interstellar space? This question unlocks a deeper scientific exploration into the very mechanics of galactic travel, challenging our models of planetary formation and stellar dynamics across the vastness of the Milky Way. Astronomers dedicate extensive research to understanding the formation pathways of interstellar objects. These rare visitors represent material ejected from distant star systems, launched into the galactic void through powerful, often violent cosmic events. The journey begins with an escape, a phenomenon far more common in the early chaotic stages of stellar system development than in their mature phases. Understanding these ejection mechanisms is crucial to tracing the potential birthplace of 3I Atlas, and indeed to comprehending the true population of free-floating bodies in our galaxy. Each interstellar object detected offers a unique window into the processes occurring within other stellar nurseries, allowing us to sample material from worlds we can never directly observe. One primary mechanism involves the intricate gravitational dynamics within nascent planetary systems. A young star, still surrounded by its protoplanetary disk, hosts numerous planetesimals and forming planets, all engaged in a complex, often unstable gravitational ballet. Over time, as gas giants grow, their immense gravity can dramatically alter the orbits of smaller bodies. Close encounters between a smaller body, like a growing comet or asteroid, and a massive gas giant, for instance, can act as a powerful gravitational slingshot. This process involves an exchange of angular momentum, where the larger planet loses a tiny fraction of its orbital energy, imparting immense kinetic energy to the smaller object. This gravitational kick can propel a body to velocities exceeding the escape velocity of its home star, sending it hurtling beyond the reach of its stellar parent and into the cold, dark expanse between stars. Simulations show that systems with hot Jupiters, massive gas giants orbiting very close to their stars, are particularly efficient at ejecting material due to their strong, disruptive gravitational influence on inner system dynamics. Such events are not mere theoretical constructs. They are observed in sophisticated simulations of early solar system evolution, where significant numbers of icy and rocky bodies are gravitationally ejected, destined to become interstellar travelers. Another incredibly potent source for interstellar ejecta lies within the chaotic dance of binary or multiple star systems. These stellar configurations, where two or more stars orbit a common center of mass, create highly complex and inherently unstable gravitational environments. The intricate, often unpredictable interactions between these stars can violently destabilize nascent planetary systems or dense asteroid belts. This gravitational turbulence acts like a cosmic pinball machine, where bodies are repeatedly perturbed, gaining velocity with each close pass. Such systems are considered prolific ejectors, capable of launching a significant fraction of their forming planetesimals and even fully formed planets into interstellar space. The constant gravitational perturbations provide a continuous and powerful mechanism for accelerating objects to velocities far beyond their escape limits. Given that a substantial fraction of stars in the Milky Way exist in binary or multiple systems, these environments represent a vast and energetic engine for producing interstellar wanderers. The sheer violence and unpredictable nature of these gravitational billiards make them prime candidates for the genesis of objects like 3I, Atlas. Collisions also offer a dramatic pathway for ejection, particularly in dense, dynamically active regions. In crowded protoplanetary disks, or within early asteroid belts where material is still coalescing, catastrophic impacts between large planetesimals or even protoplanets can shatter bodies, sending fragments hurtling in all directions. If the impact energy is sufficiently high, and the trajectory of the fragments aligns correctly, these pieces can achieve escape velocity. Imagine a cosmic billiard shot, where the force of impact is so great that debris is not merely scattered, but propelled out of the entire star system. This mechanism is particularly relevant for explaining objects with unusual compositions, as deep layers of a shattered body, perhaps rich in metals or specific silicates, could be exposed and ejected without further significant processing. Such events contribute to the debris disks observed around many young stars, a testament to the ongoing, often destructive, processes of planetary formation. The energies involved in these ejections are truly formidable. Pushing the limits of gravitational physics, models suggest that the specific ejection energies required for an object to permanently escape its parent star system can be on the order of 10 to the power of 4 joules per kilogram. This figure represents the minimum kinetic energy input necessary to overcome the gravitational well of a star, pushing an object past the point of no return. To grasp this scale, consider that this is the energy equivalent of accelerating a medium-sized car to several hundred kilometers per hour, but applied to every single kilogram of a body potentially hundreds of meters across. The typical escape velocity achieved by these ejected objects often ranges from 10 to 50 kilometers per second, velocities far exceeding those of most comets gravitationally bound to a single star, and well above the average velocity of stars in the galactic neighborhood. These immense velocities are what allow such objects to traverse the vast interstellar distances, covering thousands of light-years over their lifetimes. Once ejected, the object embarks on an immense interstellar voyage, a journey spanning light-years and eons, often across the entire spiral arms of the galaxy. Its path is not a simple straight line through empty space, but a complex trajectory influenced by the subtle yet cumulative forces of the galaxy itself. Galactic tide influences, though incredibly subtle on any given moment, play a significant role in shaping its trajectory over vast timescales. The Milky Way's gravitational field is not perfectly uniform. It is a complex tapestry woven from the mass of billions of stars, vast clouds of gas and dust, and the pervasive, unseen influence of dark matter. This non-uniformity means that as an object moves through the galaxy, different parts of its trajectory experience slightly varying gravitational pulls from the collective mass of the galaxy. These minute gravitational tugs, acting over millions of years, guide the object like an unseen hand, subtly altering its velocity vector and orbital inclination within the galactic plane. The average acceleration caused by these galactic tides is approximately 10 to the power of -13 meters per second squared. This minuscule force, imperceptible on human timescales or even over a human lifetime, cumulatively alters the path of interstellar objects, directing them through the galaxy's grand spiral arms, influencing their orbital eccentricity within the galactic disk. It is as if 3I, Atlas, is riding imperceptible cosmic currents across the Milky Way. Its journey far beyond a single planetary system, influenced by the very structure of the galaxy itself, a silent testament to the pervasive power of gravity. The duration of this cosmic journey is almost unfathomable, stretching beyond any human comprehension of time. Academic models indicate interstellar travel durations, ranging from 10 to the power of 8 to 10 to the power of 9 years. This means the object has been adrift for hundreds of millions to a full billion years, a period that dwarfs the entire history of complex life on Earth and comfortably predates the formation of many of the stars we see tonight. You watch the slow, inexorable drift across the galactic disk, a silent testament to cosmic endurance and the vastness of cosmic timescales. The origin system, if it still exists, would be utterly transformed, its stars having lived and died, its planets perhaps long gone, leaving no trace of the violent genesis that launched 3I, Atlas, on its lonely path. Such immense travel times also imply that the object could have originated from almost anywhere within the galactic disk, making its precise source system nearly impossible to pinpoint. Yet, a profound academic tension persists when considering 3I, Atlas, particularly when trying to reconcile its observed characteristics with these widely accepted ejection models. Its estimated size and composition, which appear to be substantial and possibly rich in refractory materials rather than purely volatiles, demand a massive source reservoir. This implies it originated from a system capable of forming large, robust bodies, perhaps a giant planet or a substantial planetesimal core. This requirement, however, often contradicts some prevailing ejection models from exoplanetary systems, particularly those that favor the easier ejection of smaller, more volatile-rich comets from the outer reaches of a star's influence. It is inherently more difficult to impart escape velocity to a larger, more massive object due to its greater gravitational binding energy. How could such a substantial, potentially rocky or metallic body achieve escape velocity from a system that could produce it without itself being torn apart or significantly altered in the process? This discrepancy fuels intense debate among astrophysicists, prompting questions about the efficiency of ejecting truly massive objects. Could its very nature, its substantial mass and implied resilience, point to a different, more violent genesis than a simple planetary slingshot, perhaps a direct stellar encounter or a hypervelocity collision? Interestingly, some simulations suggest that objects ejected from binary star systems might actually be more likely to carry unusual compositions. The extreme gravitational forces and frequent high-energy interactions within these systems can violently perturb protoplanetary disks, dredging up deeper, less processed materials from a forming planet or planetesimal. These materials, often richer in silicates, metals, or even exotic compounds, might otherwise remain buried deep within a planetary body, inaccessible to standard ejection mechanisms. This offers a quirky explanation for the potential compositional anomalies of interstellar visitors, suggesting that the most chaotic and energetic environments might produce the most unusual and chemically complex travelers, providing a unique snapshot of a system's interior The journey through the interstellar medium also presents its own subtle challenges and influences, shaping the object over its long transit. While largely considered a vacuum, the space between stars contains diffuse gas and dust, albeit at extremely low densities, typically a few hydrogen atoms per cubic centimeter. These materials, over the immense distances traveled, can exert a subtle drag force, a form of cosmic friction, slightly decelerating the object over its immense journey. Radiation pressure from passing stars, though weak, can also influence its surface, potentially contributing to outgassing or surface erosion, especially for volatile-rich bodies. Furthermore, if the object possesses any intrinsic magnetization or interacts with interstellar plasma, galactic magnetic fields could also play a minor role in its long-term transport, subtly altering its orientation or path over millions of years. These minute interactions, though individually negligible, accumulate over cosmic timescales, adding layers of complexity to the object's history. Think of a message in a bottle cast into a vast, dark ocean, its journey spanning continents and centuries. It does not travel in a straight line, nor is its voyage solely determined by the initial push. Unseen currents, subtle eddies, distant winds, the gradual erosion of the bottle itself, and even chance encounters with passing ships all conspire to guide its path over immense distances and unfathomable durations. Similarly, interstellar objects are subject to a complex interplay of forces, each contributing to their long, meandering voyage across the galaxy. A journey whose true history is etched into their very structure, a cosmic fingerprint waiting to be deciphered. What kind of cosmic crucible forged this wanderer, shaping its trajectory and composition over eons? What unknown worlds did it leave behind? A silent witness to its violent departure, carrying echoes of its distant home, perhaps even fragments of its parent star. These questions of origin and journey are complex, weaving together planetary science, stellar dynamics, and galactic evolution. They compel us to look beyond our own solar system for answers, to consider the full range of possibilities that the vast, dynamic universe presents. They lead us directly into the scenarios and implications we must now consider, as the very existence of 3I, Atlas challenges our understanding of the universe and the violent, beautiful processes that populate it. The intricate dance of orbital mechanics, once a predictable waltz for 3I, Atlas, now reveals discordant notes, echoing through the vast, cold emptiness it traverses. Its journey, initially charted with confident precision through years of astrometric data, has begun to show deviations, subtle but persistent, prompting a profound re-evaluation of every established assumption regarding interstellar visitors and the very nature of cosmic wanderers. You watch the latest telescopic data stream across monitors in hushed control rooms, where the only sound is the low thrum of cooling fans and the occasional click of a keyboard. High-resolution spectrographs, meticulously calibrated against known stellar standards and cross-referenced with laboratory simulations of extreme environments, capture the faint, scattered light from 3I, Atlas. These instruments reveal subtle shifts in its spectral signature, a deepening mystery etched into the very photons reaching Earth. A faint reddish hue begins to dominate the coma, replacing the expected icy blue of typical cometary outgassing. This color change is not merely aesthetic. It suggests the pervasive presence of complex organic molecules, specifically tholins, far beyond the simple water ice and carbon dioxide usually observed in comets. Tholins, known for their dark, reddish appearance, typically form when atmospheric gases are irradiated by intense ultraviolet light or charged particles, often in methane or nitrogen-rich environments. Their detection here, at such a great distance from the Sun, approximately 4.5 astronomical units, implies a more active, dynamic internal environment than previously modeled, or perhaps an origin in a dramatically different stellar system with unique radiation conditions and primordial compositions. The specific absorption bands in the infrared spectra, centered around 3-4 micrometers, strongly point to a prevalence of nitrogen-rich compounds and polycyclic aromatic hydrocarbons. Characteristics almost unknown in objects originating from our own solar nebula, which tends to favor oxygen-rich species. This spectral anomaly alone represents a significant challenge to existing cometary formation theories. Furthermore, unexpected chemistry unfolds within the object's expanding atmosphere, defying thermodynamic expectations for its environment. Astronomers detect an increasing abundance of heavy hydrocarbon chains. Compounds like ethane, CO₂-rich, propane, C3H8, and even more complex, unsaturated molecules such as benzene, C6H6, and toluene, C7H8. These compounds possess higher molecular weights and more complex bonding structures than typical cometary volatiles. They are rarely stable in the frigid vacuum of deep space, especially at such vast distances from the Sun where solar heating is minimal. Their sustained presence suggests an internal heat source, or a highly efficient, ongoing chemical synthesis, perhaps driven by cryovolcanic activity beneath a surface crust. This departure from the typical sublimation of primordial ices challenges fundamental cometary science. The observed ratios of these complex organics to simpler volatiles like water, H2O, or carbon monoxide defy established cometary composition models, pushing the boundaries of known astrophysical chemistry. The sheer volume of these complex molecules, estimated to be hundreds of kilograms per second, requires an energy source and a chemical factory that current cometary physics struggles to explain. Specialized instruments on the James Webb Space Telescope, with its unparalleled infrared sensitivity, have confirmed these unusual molecular signatures with unprecedented clarity, adding significant weight to the anomalous findings and ruling out many instrument-based error possibilities. The persistent presence of these heavy molecules, despite their vulnerability to photodissociation by solar radiation and cosmic rays, adds another layer of profound mystery. The tale of 3I, Atlas, once a modest plume stretching tens of thousands of kilometers, now elongates with surprising vigor. Its growth rate accelerates dramatically, pushing past established models for cometary outgassing. Typically, a comet's tail length is directly proportional to its volatile production rate and its interaction with the solar wind. For 3I, Atlas, the observed growth rate, sometimes exceeding 100,000 kilometers per day, far surpasses what its current heliocentric distance and estimated size should allow. This rapid expansion hints at a sudden, internal activation, a release of energy or material that seems disproportionate to its environment. The non-gravitational forces acting upon 3I, Atlas, derived from precise astrometric measurements, are significantly higher than expected for its estimated mass and activity level. This suggests a powerful directed expulsion of material, rather than a uniform sublimation. It is as if a switch has been flipped in the profound darkness of interstellar space, initiating complex processes unseen in any known comet from our solar system. This object, 3I, Atlas, appears to be evolving, undergoing a transformation that defies conventional understanding, hinting at an internal engine or a programmed sequence of events. The sheer scale of this activity, sustained over weeks and even months, suggests a vast, perhaps renewable, reservoir of energy or a novel mechanism for its controlled release. Comparisons to the most active comets in our solar system, such as C 2014, UN 271, Bernardinelli-Bernstein, or the Great Comet C 1995, 01 Hale-Bopp, show that even their extreme outbursts pale in comparison to the sustained, anomalous activity of 3I, Atlas, at similar solar distances. One peculiar observation notes a transient, rhythmic fluctuation in its brightness, almost like a slow, deliberate pulse, lasting for several hours before fading into the background noise. This subtle periodicity, detected by multiple observatories using precise photometric techniques across various wavelengths, does not align with simple rotational tumbling or irregular outgassing. The period of this pulse was approximately 4.7 hours, with a brightness amplitude variation of about 15%, a significant and repeatable signal. While some suggest it could be a complex interaction of gas jets and dust, perhaps from a highly fractured nucleus experiencing periodic venting, others postulate a more structured, internal mechanism at work, possibly involving a precessing spin axis or internal fluid dynamics. Attempts to correlate this pulse with known rotation periods of similar objects or with specific volatile sublimation rates have yielded no definitive, natural explanation that fully accounts for its regularity and amplitude. This quirky detail, a fleeting cosmic heartbeat, adds another layer to the enigma, suggesting a level of internal organization or dynamic stability not expected from a primordial ice ball. The persistence of this signal over multiple observation windows, spanning weeks, has further deepened the mystery, making random chance or observational artifact increasingly unlikely. This cascade of anomalies triggers a new layer of profound concern among a subset of researchers, pushing the boundaries of scientific caution into realms once considered purely speculative. What if 3I Atlas carries more than just volatile ice and dust, remnants of a distant stellar nursery? What if it harbors embedded fragments, perhaps even small dense debris, shielded within its outer layers, designed for release at specific junctures in its journey? A worst-case model considers the possibility of these fragments being ejected with significant velocity, perhaps through controlled vents, a sudden, energetic targeted outgassing event, or even a deliberate structural failure. Should such debris intersect with the orbital path of Mars, or even Earth, the implications could be profound and catastrophic. Consider the potential for meteor showers, dust particles, even microscopic ones, entering an atmosphere at extreme speeds, exceeding 60 kilometers per second, could spark unprecedented meteor showers. These would be far more intense than any recorded historical event, potentially saturating the upper atmosphere with incandescent trails. The sheer kinetic energy of these particles, even at micron scales, would create a dazzling yet potentially hazardous display, disrupting satellite communications and posing risks to space-based assets. Larger fragments, perhaps meters in diameter, represent a low probability but high consequence impact risk. A fragment, merely 10 meters across, traveling at interstellar speeds, could release kinetic energy equivalent to several kilotons of TNT upon atmospheric entry, similar to the Chelyabinsk event in 2013, which shattered windows across a wide region. Such an airburst could cause widespread damage to infrastructure, trigger secondary fires, and pose a direct threat to life. While unlikely, the possibility of an object like 3I Atlas, with its unusual behavior, carrying such a hidden payload, cannot be entirely dismissed by the most cautious models, especially those considering the controlled object hypothesis. For Mars, even small impacts could alter its tenuous atmosphere, contaminate potential subsurface water ice reservoirs, or even damage future robotic missions. The sheer unpredictability of such an event given the object's anomalous nature, is a source of quiet anxiety. Imagine a scenario where 3I, Atlas, this controlled object as some theorize, deliberately releases these smaller components. This concept, while speculative and bordering on science fiction, adds a chilling dimension to its observed behavior. Could these ejected fragments be an unreadable message, a form of interstellar communication we cannot yet decipher, designed to interact with planetary magnetospheres or atmospheres? Perhaps they are intended to seed planetary environments with exotic compounds, altering their chemistry as a precursor to some larger, unknown agenda. The very notion of a controlled object implies intent, a purposeful manipulation of its trajectory or composition, or even a pre-programmed sequence activated upon entering a new star system. This shifts the debate from natural, albeit extreme phenomena, to something far more deliberate, far more unsettling, hinting at a hidden truth scenario where our understanding of cosmic visitors is fundamentally incomplete. The implications of such a deliberate act, even if currently undetectable, are vast and unsettling, challenging our perception of cosmic solitude and our place within the universe. This hostile vessel logic, though extreme, forces a re-evaluation of all incoming data, searching for patterns that might betray an artificial origin, however subtle. Could it be a probe designed to gather data or even influence solar systems it encounters? The very idea, whispered in darkened observatories, demands a rigorous yet open-minded scientific inquiry. However, the moderating counterview firmly grounds itself in current observational data and established physics, maintaining a rigorous adherence to Occam's razor. Despite these intriguing anomalies, 3I, Atlas continues its journey along a meticulously defined trajectory, precisely tracked by global networks of telescopes, including the ESA's Gaia mission for stellar background referencing and the Pan-STARRS survey. Its closest approach remains well outside Earth's orbital plane, at a minimum distance of approximately 0.2 astronomical units, or about 30 million kilometers. This distance is substantial, providing a wide safety margin far beyond any immediate threat of collision for Earth or Mars. Planetary defense systems, while vigilant and continuously updating their models with new astrometric data, report no immediate threat. The observed changes, while unusual, could still represent extreme, yet natural, cometary behavior, perhaps from a composition never before encountered in our solar system. Its high velocity, approximately 55 kilometers per second relative to the Sun, ensures a rapid transit, minimizing prolonged interaction with the inner solar system and reducing the window for any significant gravitational perturbation or interaction. The current models, based on extensive astrometric data collected over many months and corroborated by multiple independent observatories, to show no deviation that would place it on an impact course with any inner solar system body. The error bars on its trajectory are now remarkably small, on the order of hundreds of kilometers over millions of kilometers of travel, making any sudden, unpredicted, natural deviation highly improbable. Furthermore, comparisons to other unusual comets, such as 2I, Borisov, which also displayed peculiar outgassing, show that while 3I Atlas is more extreme, it might still fall within the very broadest definition of natural cometary activity. If one considers an origin from an exceptionally cold, chemically distinct stellar nursery, the scientific community has a long history of encountering phenomena that initially defy explanation, only to later find a natural, albeit complex, physical process. The academic tension remains palpable, a quiet hum beneath the surface of scientific discourse, a profound division in interpretation that permeates conferences, preprint servers, and late-night discussions, Is this visitor benign? A unique interstellar wanderer, offering unprecedented insights into cosmic chemistry and the diversity of stellar nurseries across the galaxy? Or is it a harbinger of unknown phenomena? A silent messenger carrying implications we cannot yet read? A signal from the deep dark that challenges our very definition of what a comet can be? This unresolved debate echoes through observatories and research institutions worldwide. A fundamental question without immediate, definitive answers. Some researchers cautiously explore the fringes of what constitutes natural phenomena, proposing exotic ice compositions, complex internal fracturing, or even highly unusual past interactions with other stellar bodies. Others insist on adhering strictly to known physics, even when observations stretch those boundaries, arguing for extreme but natural explanations and warning against premature conclusions. The burden of proof for extraordinary claims, they contend, remains exceptionally high, demanding irrefutable evidence before considering non-natural origins. This intellectual struggle between cautious empiricism and speculative theorizing defines the current understanding of 3I, Atlas, creating a quiet yet intense academic battlefield. It is as though a faint, unknown melody has begun to play in the cosmic silence, its notes both beautiful and unsettling, hinting at a composer or a process beyond our current comprehension, a score written in the very fabric of space and time, yet only now becoming audible to our most sensitive instruments. What if the very act of observing 3I, Atlas, with our powerful instruments and focused attention across the electromagnetic spectrum, is part of a larger, pre-programmed interaction, inadvertently triggering its hidden processes or revealing its true, complex nature to an unsuspecting audience? The implications of such profound uncertainty ripple through the quiet halls of scientific inquiry, demanding vigilance, fostering deep philosophical reflection, and compelling a re-evaluation of our most fundamental cosmic assumptions. This enigmatic visitor continues its silent passage, leaving behind a trail of unanswered questions and a growing sense of cosmic wonder, its true purpose still obscured by the vastness of space and the limits of human perception. It moves onward, a dark enigma against the starlight, its secrets still tightly held, pushing the boundaries of our cosmic understanding. As the data continues to accumulate, the narrative surrounding 3I, Atlas, shifts from mere observation to profound interpretation. The object's behavior deepens its mystery with each passing day. You watch as its coma exhibits a startling dominance of carbon dioxide. This chemical signature presents a significant puzzle to astronomers worldwide. It suggests a volatile composition quite unlike typical solar system comets. Then, a distinct tail begins to form, yet its formation dynamics defy easy classification. The spectral slopes, consistently redder than expected, further deepen the enigma. These rapid changes, this unpredictable evolution, push the boundaries of conventional cometary science. Each new data point seems to add another layer to an already complex celestial riddle. The sheer unusualness of these observations invites speculation, drawing some minds towards truly unconventional explanations. A daring hypothesis emerges within certain circles. What if 3I, Atlas, is not a natural comet at all? Imagine a technological artifact, meticulously disguised, traversing the interstellar void. Its cometary facade, a clever deception, could mask an entirely different purpose. This scenario entertains the possibility of an artificial origin. It suggests a crafted object rather than a mere agglomeration of ice and rock. You find yourself peering through a keyhole into alien architecture, you glimpse a design potentially beyond terrestrial understanding. The worst-case model postulates deliberate maneuvers. It suggests subtle course corrections, perhaps unseen by our current instruments. This view imagines hidden propulsion systems, silently guiding the object. It could be executing a calculated pass-through of our inner solar system. This perspective transforms 3I Atlas from a passive cosmic wanderer. It becomes an active participant in an unknown cosmic agenda. One peculiar observation notes the precise timing of certain outgassing events. These seem almost triggered by specific orbital positions. They do not appear to be merely a result of thermal exposure. The idea of a sleeper craft, dormant for millennia, now subtly active, enters the discussion. If this visitor is indeed artificial, its implications are staggering. Could it be a message craft, deliberately sent across light years to announce a presence? Perhaps its anomalies are not malfunctions at all. They might be encoded signals, waiting for decipherment by a sufficiently advanced intelligence. The very act of its passage might be a form of communication. It could be a cosmic billboard, silently broadcasting its existence. Such a discovery would fundamentally alter humanity's place in the cosmos. It would shift our understanding from solitary existence to a universe teeming with intelligence. The search for extraterrestrial life would suddenly find its subject within our grasp. It would be an object we could potentially study up close. Yet, against these profound imaginings, the scientific community grounds itself in known physics. Many astronomers emphasize conventional natural processes. They argue that even the most unusual phenomena can be explained. The universe is vast, and its natural processes can often mimic the complex. An object ejected from a distant planetary system, perhaps under extreme conditions, could present such signatures. Consider a rogue planetesimal, subjected to intense radiation near its parent star, or imagine a fragment from a highly processed, carbon-rich protoplanetary disk. These scenarios offer explanations rooted firmly in astrophysics. They do not require invoking alien technology. The unusual CO₂ dominance might arise from a unique formation environment. Perhaps it formed in an exceptionally cold region, far from its star. Its red spectral slopes could indicate particular tholins, or complex organic molecules. These are substances known to form under specific interstellar conditions. The rapid changes might be due to a highly fractured nucleus, exposing fresh volatiles, or perhaps a tumbling rotation presents different facets to the Sun at varying times. The sheer diversity of interstellar objects, still largely unknown, allows for extreme variations. To attribute every anomaly to artifice risks, overlooking genuine new astronomical discoveries. These could be breakthroughs in understanding cometary evolution. The academic tension mounts. Do we interpret these anomalies as groundbreaking new science, pushing the boundaries of cometary understanding, or as wild, unproven speculation? This debate highlights the core challenge of scientific inquiry. It forces us to confront the truly novel with both open minds and rigorous skepticism. The data from 3I Atlas forces a confrontation between the known and the radically unknown. It challenges our preconceived notions of what a comet can truly be. The object remains a silent observer, yet its presence sparks a fervent internal dialogue across the globe. You are left to ponder the nature of discovery itself. How do we distinguish between an extreme natural outlier and something truly alien? The line blurs, inviting both rigorous analysis and imaginative contemplation. What if the visitor, silently charting its course, holds secrets far grander than mere ice and rock? Secrets that could redefine our cosmic destiny. The shadow of what 3I Atlas might represent, a fleeting whisper of the truly unknown, compels you to consider the necessary shifts in our cosmic vigilance. This object, with its unexpected accelerations and sudden bursts of activity, redefines the urgency of our planetary defense protocols. Astronomers note that the rapid changes detected within 3I, Atlas, demand an entirely new paradigm for monitoring interstellar visitors. The observational cadence for any newly detected interstellar object must now increase dramatically. What was once deemed sufficient, perhaps a scan every few days, proves inadequate for phenomena like 3I, Atlas. Daily, even sub-daily, scans become a critical requirement. This intensified scrutiny necessitates a global network of telescopes. Operating with seamless coordination, you watch as data streams from facilities like the Pan-STARRS surveys, the ATLAS system, and the Zwicky transient facility, all feeding into a unified alert system. The sheer volume of incoming telemetry, coupled with the need for immediate analysis, strains existing infrastructure. Dedicated telescope time, previously allocated for routine sky surveys, would need reassignment for these high-priority, transient events. The challenge lies not just in detection, but in the sustained, high-resolution follow-up required to characterize such dynamic objects. Follow-up strategies for these enigmatic voyages require unprecedented inter-agency data sharing. The silos of national observatories and space agencies must dissolve into a common pool of knowledge. NASA, ESA, JAXA, and national facilities like ESO's Very Large Telescope or the Gemini observatories must establish robust, real-time data exchange protocols. Imagine a secure digital platform where spectral data from Mauna Kea merges instantly with astrometric measurements from Chile. This collaborative framework extends beyond raw data. It includes shared analysis tools, joint scientific working groups, and unified communication channels. The goal is to synthesize disparate observations into a coherent, actionable understanding, bypassing bureaucratic delays. Such cooperation ensures that every precious observation window, often measured in hours or even minutes, contributes to a collective insight. The alert thresholds for unusual interstellar objects require a fundamental reassessment. Current criteria, largely tailored for near-Earth asteroids and known comets, simply do not capture the unique signatures of objects like 3I, Atlas. A high eccentricity alone is insufficient. Instead, new triggers must include sudden, significant changes in brightness, unexpected non-gravitational accelerations, or the rapid appearance of a cometary tail, where none was predicted. These anomalies should elevate an object to a priority status, demanding immediate, intensive follow-up. The definition of unusual expands to encompass any behavior that deviates from established cometary or asteroidal models, particularly for objects exhibiting interstellar trajectories. This proactive re-evaluation aims to prevent critical information from being overlooked in the noise of routine astronomical discoveries. Deflection and response concepts, while not immediately applicable to 3I, Atlas, due to its trajectory, become a vital, if theoretical, policy discussion. The very existence of an object capable of rapid, unpredictable changes prompts questions about future interstellar threats. What mechanisms could be deployed if a similar but directly hazardous object were detected on an impact course? Kinetic impactors, gravitational tugs, or even directed energy systems, all designed for slower, more predictable asteroids, face immense challenges when confronted with a fast-moving, potentially small, and dynamically evolving interstellar body. The ethical considerations of intervening with an extraterrestrial object, even one posing a threat, are profound. International policy frameworks must begin to address these hypothetical scenarios, establishing clear lines of authority and responsibility for any potential intervention. As if erecting a sentinel post at the edge of our solar system, humanity must map not just the discovery of these objects, but also the comprehensive, multi-layered response. This involves not only technological upgrades, but also a profound shift in interagency trust and collaboration. One quirky detail illustrates the fleeting nature of these observational opportunities. The dramatic tail growth of 3I Atlas was captured with a mere 30-minute exposure on Gemini South, a stark reminder of how narrow these windows can be before vital information vanishes. This urgency highlights a persistent academic tension. Readiness often lags significantly behind the speed of discovery. The scientific community grapples with the need to develop agile response protocols that can match the pace of unexpected cosmic events. This new reality, illuminated by 3I Atlas, shifts our gaze toward a deeper resolution. After the urgent discussions of readiness and response, our gaze now returns to the departing visitor. In the stillness that follows the intense tracking of 3I Atlas, you sense the profound echo of knowledge gained, yet also the persistent hum of questions left unanswered. This enigmatic object, a true interstellar wanderer, has completed its silent transit through the inner solar system. It arrived from the vast, unknowable gulf between stars, a cosmic voyager briefly illuminated by the distant warmth of our sun. We diligently tracked its every subtle shift, noted its unexpected accelerations, and pondered its puzzling behaviors. Each observation, each spectral signature, each deviation from expected paths seemed to peel back a layer, revealing an object unlike any we had encountered before. Its journey through our celestial neighborhood became more than a mere scientific event. It transformed into a mirror, reflecting both the sharp edge of our scientific prowess and the profound depths of our cosmic limitations. The data gathered, though incomplete, whispers of distant systems, of diverse chemistries born in alien nebulae, and of ancient journeys spanning millennia across the galactic plane. We grappled with the implications of its rapid changes, sensing in its movements a certain, deliberate nature, a controlled trajectory that defied simple cometary physics. This object, whether a natural marvel or a sophisticated construct, reshaped our understanding of what might lie beyond the familiar confines of our home star. It carried with it secrets of other suns, other worlds, perhaps even the silent testament of other intelligences. Its fleeting passage has etched a new and expansive perspective into the collective human consciousness, a realization of the universe's boundless potential for the unexpected. You watch now as 3I Atlas, its brief, mesmerizing performance concluded, begins its long, quiet fade. It becomes a diminishing point of light, steadily swallowed by the immense, indifferent darkness of interstellar space. It is as though a torch, carried across an immense, star-strewn chasm, flickered brightly for a precious moment, then was gently, irrevocably extinguished. The light it cast upon our understanding, however, remains a permanent illumination in the corners of our minds. One profound question lingers, echoing softly in the quiet vacuum of its departure. Will the next interstellar visitor arrive even stranger, even more enigmatic, even more challenging to our assumptions than 3I Atlas? So it drifts, a silent messenger on a luminous trail, carrying its untold story into the endless dark, leaving only the profound and haunting echo of its passage across the void.